Hello. Hello. Wanted to start the opening remarks for the Resource Constrained Learning and Wireless Networks workshop. So my name is Irvin Moore. I'm a PhD computer science student at FIU, and I will help host this workshop. So this workshop seeks to bring ML and wireless networking experts together to identify interdisciplinary approaches to evolve ML algorithms for and over communication networks that operate under constrained resources, including time, labeling, and computational capacity constraints. This workshop will provide a unique opportunity to expose the MLSys community to the challenge and opportunities of integrating ML models into resource-constrained communication networks. This will also highlight emerging trends in ML with limited resources and their implications for their design and operation of next-gen communication networks. So this is the Resource Constrained Learning and Wireless Networks workshop. And we are going to get started in a few minutes with our first speaker, Haiji Kim. And I will introduce that in a few minutes. Hi, Haiji. Can you share screens? Is everything working? Great. Yeah, thank you. Conference. One word, all lowercase. Okay, so I will start by introducing Haiji Kim from the University of Texas at Austin. So Haiji Kim received the PhD degree in electrical engineering from Stanford University in 2016. She is an assistant professor with the Department of Electrical and Computer Engineering at the University of Texas at Austin. She worked as a postdoctoral researcher with the University of Illinois at Urbana-Champaign from 2016 to 2018. She worked as a researcher with Samsung AI Research Cambridge from 2018 to 2020. At UT Austin, she is a member of the Wireless Networking and Communications Group, 6G at UT, and the Machine Learning Laboratory. Her research interests include information theory, coding theory, machine learning, and wireless communications. So, Haiji Kim, welcome, and after you.
All right, thank you so much. And thanks very much for the invitation to give a talk at this workshop. It's my great pleasure. I wish I were there, but I'm in Korea right now. So apologies for having it virtual. Okay, so my talk today is gonna be on learning context context-dependent CSI feedback by cluster federative learning. This is a very, very dense title, so I will parse them one by one. And this is joint work with my colleague Gustavo Di Vicena and our code by the Haesung Kim, and this is supported by Interdigital. Okay, right. So okay, so just to begin with the motivation of the work. So the motivation for this work was wireless applications. We were thinking about distributed coordinated multipoints. For those of you who are not familiar with this, what this means is that, let's say in cellular communications, there are multiple base stations around. And then what we want is this base stations somehow share information among themselves and coordinate to have better management of the wireless system. So essentially, we want base stations to talk to each other and have some coordination. And why do we want to do that? Because if they talk to each other, then they can do nice things. For example, they can try to avoid interference for the cell edge users. So that's a nice thing. But the key enabler for the coordinated multipoint really is the channel state information. So the base station has to know the channel for all the wireless devices. And that's actually a pretty challenging task because the channel state information usually is a high dimensional vector. So the channel state information, in short, CSI channel state information can easily be like 30,000 complex values. So it's a very high dimensional amount of data. And under the resource constraint setting, we cannot quite convey the channels the information as is. So what we need to do is we want to somehow compress the CSI. We want to somehow compress the channel state information. And recently, it's shown that we can do this using neural networks. So we can learn to compress the CSI information, and that is shown to outperform the analytical baselines. This research started around like 2018, 2017, called CSINet. And we also have a work in the space. And this is also one of the study items in the 3GPP Wireless Communication Society. That's good. So I mean, we have some results. CSI compression works well, and so on and so forth. So then are we done? Now, can we use the CSI compression networks in reality? Not really. There are still two major challenges, okay? So the first challenge is that the channels that the mobile devices are gonna encounter are very diverse. So the mobile devices are also called the user equipment. So user equipment devices will encounter diverse channels. Maybe sometimes it's in the residential area, sometimes it's in the park or commercial area, and so on and so forth. So then what can we do? Well, a naive approach one can think of is just ignore the diversity and then use an encoder and decoder, the CSI compression encoder and decoder for any scenario. That's one possible approach, but that's not so much desired because that will potentially mean that we want to have an encoder and decoder that's highly capable, potentially very large, to accommodate all the diverse situations. On the other extreme, we may think about, well, let's learn different pair of encoders and decoders for all sorts of scenarios. So we learn an encoder and decoder for a commercial area, we learn an encoder and decoder for a park area, learn an encoder and decoder for residential area, and so on and so forth. And that's also not so much desired because the issue here is that the mobile devices are like moving around, and having to carry all the different encoders is a huge burden. So what we propose instead is we are gonna have a universal CSI encoder, and we are gonna let the decoder to be diverse. So that's our proposal here. So we wanna have the UE, the users, mobile devices, carry one encoder, and the base station, the decoder side, has multiple small decoders, different decoders for different channel environments. So then are we done yet? Well, not quite, because another big challenge, the real challenge I want to talk about today is the training data, the amount of training data is limited. And this is especially so for the CSI compression problem, because collecting the raw CSI, the uncompressed CSI, requires a lot of data collection, and that's an expensive operation there. So the scenario here is we want to train the CSI compression network, but the amount of data set is highly limited. So then what can we do? Okay. So what can we do? Well, one thing we can do is we can look around, right? We can look around and then we can try to do some sort of collaborative learning. So maybe like I have this commercial area here, but maybe there's some other commercial area there, in which case we wanna sort of like collaboratively learn CSI compression method or any neural networks, right? And that's that's if there is no privacy concern, well, everyone can just send their data and then learn a model based on the data set from all the for everywhere. But that's not so much possible because of the privacy concern. And when there is a privacy concern, the common framework we resort to is the federative learning, right? Federative learning allows us to keep the data local while allowing the collaborative learning environment. So that's the thing. But one issue is that if we do the federative learning and learn a common model, right? Common model, global model for every possible scenario, that's not great because that will mean that we use the same CSI compression networks for residential area versus park versus like mobile users and so on and so forth. That's not what we want. So what we propose to do is the following. We want to do the federative learning, but we want to do the clustered federative learning. So here we have two goals. One is we want to cluster these locations based on the context. For example, I want to sort of group the parks here and the parks there together because they are similar parks. And then maybe residential areas and commercial areas are sort of similar, in which case I want to group them together into one context. That's what we want to do. So we want to cluster the locations based on the context. And then for each context, we want to learn a CSI compression network. Okay, so that's our goal. So we want to learn a context-dependent CSI compression methods in a federative learning manner. So before I get to the details, I want to talk about some overview on the cluster federative learning. We are not the first to think about the cluster federative learning. There has been several studies. Unlike federative learning, where the goal is to learn one global model for all the clients, in the cluster federative learning, we are envisioning a scenario where there are clients with clusters of clients, meaning maybe there are some like two clients here who have the red-ish distributions, while the other two have bluish distributions. In which case, what we would like to do is we want to sort of group the red users together and the blue clients together, and then learn one model for the red distributions and another model for the blue distribution. That's what we want to do for the clustered federative learning. And more formally, just to state the setup here, let's say we have C clients, and each client has data generated from data distribution D sub C. And now we let F of D sub C comma theta denote the C client's loss on the model theta. Then in the CFL, clustered federative learning setup, what we aim to do is we want to find two things, okay? Two things. One is we want to find the clustering of the C clients into, say, K clusters, K groups. And then we want to learn one model for one group, one model for one cluster. So we want to learn K models, okay? In a way that we minimize the sum loss. Okay, the sum loss meaning sum of the loss for all the C clients. And when we evaluate the C client's loss, we are going to evaluate the loss on the model theta where the client C is assigned to. So this pi of C denotes the cluster identity or clustering of the C clients. Okay, and then what's key is we want to do this without having direct access to the data samples or distributions. Okay, in the interest of time, I'm not gonna go through the details of the existing work, but there are very nice works already, like IFCA and MADMO. and they have theoretical guarantees, very nice guarantees. But one challenge we found is when we apply these algorithms to the CSI compression setup, they did not work that well. That main challenge here is that we are looking at the regime where there are like tens to hundreds of clients, and these existing algorithms tend to work very well when you have a lot of clients, like thousands, more than 100 clients. So we need a new cluster federated learning algorithm, and that's where we are heading to. Okay, so we proposed a new solution, a new cluster federated learning CFL algorithm that leverages the gradient space partitioning. So as you might guess, we are leveraging the gradients. But before I talk about any of that, let me first give a high-level overview of how this algorithm works. Okay, so as I said, there are two things we have to update during the learning procedure. One is the clustering of the clients, and then the other is the K models. So we have to update clustering and models. So what we do is we make this iterative. So we will iterate between the update of the models and update of the clustering. And then we will update the clustering only periodically, because once we update the clustering, we sort of believe on the cluster. So we'll update the model a few times, and then later we will revisit the clustering and then see if we can make it better. That's a high-level idea. And then the key question is, so how do we cluster the clients when we don't have access to the raw data? That's the core question we're going to talk about next. Okay, so right, so I'm gonna give a running example here. So let's say we have 3 clients. Client 1 and 2 have similar distribution, let's say D sub A, and the client 3 has another distribution, DB. So we have 2 clients with common distribution, another client with its own distribution. And suppose the central unit now wants to learn 2 models. Okay? So 2 models, then ideally what we want to see is we want to learn a blue model that's shared between the clients 1 and 2, and the red model that's assigned only to client 3. That will be ideal. And then this will be easy if we have access to the data distributions or the data samples, but we don't have access to any of that. Instead, during the federated learning procedure, what we have is their gradients. So we don't have, by we, I mean the central unit. Central unit does not have access to the distributions, but it has access to the stochastic gradients and the loss values. Okay. So now the question then is, okay, now that the central unit has stochastic gradients, can we use these gradients as a feature for clustering? These gradients are actually very high dimensional, right? So potentially the gradients can be quite informative. So now let me explain why this should work. Okay, so observation number 1. Let's think about the loss function. Okay, so when we think about the loss function for, say, clients 1 and 2, they have the same data distributions. So if you think about, say, the population loss, they should have the same loss or very similar loss. On the other hand, the client 3 who has different data set will have different loss functions. So, okay, so clients with similar data sets should have similar loss functions. That's our premise here. And then they will also imply that the clients with similar data sets should have similar gradients. So there we go. So we see that the clients with similar data sets should have similar gradients. So then are we done? Well, let's just use gradients for clustering. Are we done? Well, no, there are 2 issues. Number 1 is that the gradients can be noisy because the clients have limited amount of data, and stochastic gradients are gonna be noisy. Meaning, even though the population loss function for, say, D sub A and D sub B are sufficiently far away from each other, when we measure the gradients based on the limited amount of data samples, we're gonna see the noisy version of the population gradient, right? So potentially what may happen is if I look at the gradient value at this data point here, I cannot quite say the client 1 and 2 have similar data distributions because like client 1 and 2 and 3, they all have very similar gradients. So clustering based on the gradients can fail potentially because of the noise in the stochastic gradients. So we have to think about how to mitigate this noise. And one thing I want to mention is the following about the distribution or the stochastic properties of the gradient noise. So there has been several studies on the stochastic gradient noise, and there has been a lot of discussion and potentially arguments and so on and so forth. But eventually, recent studies show that the gradient noise can be modeled as Gaussian, at least at the initial phase of the training. So what I mean by that is the stochastic gradient will be the population gradient plus Gaussian noise. That's a good model for the gradients. Okay. So then when we think about this, okay, so when we see a noisy observation, what can we do? We can potentially average out the noise by aggregating gradients over multiple time steps, different models, and so on and so forth. So our approach, the core of our approach is this aggregation part. Because gradients can be noisy, we are going to aggregate the gradients across time, across different models to denoise the stochastic noise. That's our key idea number one. Okay. And the next challenge is the following. The gradients are extremely high dimensional. So even though we use gradient as a feature, well, how do we cluster the client space on their gradients that are such high dimensional? And to this end, we're using the spectral clustering algorithm, which consists of two parts. One is we are doing the dimensionality reduction, and then we will do the k-means clustering. And these two are our key ideas. And we have nice theoretical and empirical results. But before I get to any of those results, I just want to reiterate the importance of the aggregation of gradients. That's really essential. So I'm gonna give you an example of the classification of the extended MLSys dataset. Here the setup is we have 160 clients in total, and 80 of them has EMList dataset, and then the other 80 clients have rotated EMList dataset. So certainly, when we learn the classifier, what we want to do is we want to learn one classifier for EMList assigned to all the 80 clients here. And then we want to learn another classifier for rotated EMList for the remaining 80 clients. That's an ideal thing to do, right? So what we are doing is the following. Over time, every once in a while, let's say at period 20, so at t equals 1, 21, 41, and so on and so forth, we are going to cluster the clients based on their gradients. Here I'm showing the projected gradients from the spectral clustering phase. So I'm projecting the gradients into, say, two-dimensional space, and then I'm showing the scatter plot for all the 160 clients. So there are 160 clients, and 80 of them have original data, so EMList. Those are shown in the orange color, and the ones with the rotated EMList dataset are shown in the purple color. So what we want to do is, what we want to see is over time, we want to see a clear separation between the orange crowds and the purple crowds. And when we do the gradient aggregation and when we do the spectral clustering, dimensionality reduction accordingly, we do see that over time, there is a clear separation between the two crowds. On the other hand, if we do not do the time averaging, it's a lot harder to see a clear separation because the noise is still hanging in there. Okay, so that's an importance, that demonstrates the importance of the aggregation. And then now I'll get to the theoretical results first. So theoretically, we show two things. One is the performance of the model, or how the model gets closer to the optimal model. So this is complicated, but what I want to say is the following. We are looking at two terms. One is the difference between the optimal model and the t-th model. And then we look at the difference between the optimal model and the t+1 model. So we want to see some contractive property, meaning we want to make sure that the difference between the t+1 model and the optimal model is smaller. It gets smaller and smaller over time. So you want to see this is smaller than the previous difference there. And then we do see that we have the difference at times that t+1 is a constant that's lower than 1 times the previous difference and some error terms. And these error terms can be mitigated by having large number of clients. And as we take time to infinity, this error term will vanish eventually. So we do see a pseudo-contractive property here. And another theoretical results is about the clustering accuracy. So the fraction of incorrectly clustered clients in our algorithm is upper bounded by 1 over in the order of 1 over batch size times time when we aggregate the gradients. What that means is that as time goes on, the probability of having the perfect clustering will go to 1, which is a nice property, I think. And empirically, we see a good performance as well. So I'm going to talk about two examples. One is the general computer vision example, and then I'll get to the CSI example later. So example number 1 is a rotated MList. So here there are 4 clusters of clients. Clients 1 to 20 has original MList. 21 to 40 has 90-degree shifted MList, and then 180 degrees and 270 degrees. There are 4 groups of clients here. And so what we want is we want to learn 4 models. One model for the 90-degree rotation, 0 degree, 270 degrees, 360 degree, and so on. So, okay. So here I'm showing the results on 2 fronts. Okay, so one of them is this coloring. So for now, let's not look at the curve. Let's look at the colors. So here, the coloring shows the clustering demonstrates clustering over time. So as time goes on, x-axis times as time goes on, what we see from our algorithm, CFLGP, our algorithm is the following. Well, as time goes on, the clustering does not change. And we see that clients 1 to 20 are grouped into cluster number 1, and 21 to 40 are clustered into cluster number 2, and then 3 and 4. So this is a correct clustering from the very first time step, and that stays as is over time. On the other hand, the baseline algorithms like IFCA, MADMO, for IFCA, they have wrong clustering. I mean, they will try to find a cluster in the beginning, and they will converge to a sort of wrong cluster, meaning clients 1 to 20 and 41 to 60 are grouped into one cluster, which is not desired. And similarly for the other baselines. And then global model here insists on having a global model for everyone. There's only one cluster. Now let's think about the accuracy here, the results there. We see that because we do the clustering correctly, the accuracy, which is shown by the curve here, labeled by the right-hand XY label there, we see that CFLGP leads to a better overall accuracy in the end. That's because we do the clustering correctly. Okay, and we also see that our algorithm works, especially when there are like hundreds to a few thousands of clients, which is relatively small. And we have some idea why this is the case. I'll be happy to talk about it. And example number 2 is the CSI compression, our initial motivation here. So here we have generated various channel data sets using the Quadriga simulator. And then we have like 5 separate clusters. And what's noticeable here is here I'm showing the data for distribution 1 versus 2 versus 3 versus 4 versus 5. They all look sort of similar. So it's very challenging to distinguish the distributions even from the samples. But we see that our algorithm tends to do the correct clustering and gets very good overall performance. And I'm not showing the baselines here, but they tend to cluster everything into one group. So our algorithm works well for when number of clients are not too many and when the distributions are all pretty similar. Even in those cases, we can find the correct clustering. Okay, so now to conclude, we began our work to address the challenges in the channel state problem, because the challenge really is that the users are going to encounter diverse channels, but we have to train the CSI compression networks using a limited amount of data sets. That was our initial motivation, and then we got to the solution using the cluster predictive learning. Especially, we proposed a new CFL algorithm that leverages the gradient space partitioning. And the key idea there is the aggregation of the gradients. And the key takeaway, I think, is the following. The stochastic gradients are like high dimensional. They are very, very informative, and they can be successfully used for cluster predictive learning. And you might be wondering about the complexity and communication cost. So what we see is, one round of spectral clustering is quite expensive. That is true, but we realized that even one round of spectral clustering tends to find the correct clustering. So if you look at the overall cost to achieve the same target accuracy, we tend to win compared to the other algorithms. And there are several other aspects we consider for improving the efficiency and complexity, but I'll probably leave it in the interest of time. And thank you very much for your attention.
Does anyone have any questions for the speaker? Anyone on Zoom have any questions? Well, I believe there's no questions. Great presentation again.
Okay, thank you.
Well, great. Our next speaker is Osvaldo Simon. He will start in a couple minutes and I will introduce him briefly.
If you give me the option to share my screen, thank you. Okay, thank you. I see it now. Great.
So I'm going to start the introduction for Osvaldo Simon. So Osvaldo Simon is a fellow IEEE who received the master's degree with honors and a PhD degree in information engineering from Politecnico di Milano in Milan, Italy in 2001 and 2005. Respectively, he is currently a professor of information engineering with the Center for Telecommunications Research, Department of Engineering, King's College London, United Kingdom, where he directs the King's Communications, Learning, and Information Processing Laboratory. From 2006 to 2017, he was a faculty member with the Electrical and Computer Engineering Department, New Jersey Institute of Technology, Newark, New Jersey, USA, where he was affiliated with the Center for Wireless Information Processing. His research has been also supported by the U.S. National Science Foundation, European Commission, European Research Council, Vienna Science and Technology Fund, European Space Agency, and a number of industrial collaborations, including with Intel Labs and Interdigital. He is also the author of the textbook, Machine Learning for Engineers, published by Cambridge University Press, 4 monographs, 2 edited books, and more than 180 research journal and magazine papers. His research interests include information theory, machine learning, wireless communications, neuromorphic computing, and quantum machine learning. He was a co-recipient of the 2022 IEEE Communications Society Outstanding Papers Award, the 2021 IEEE Vehicular Technology Society Jack Bauer Memorial Award, the 2019 IEEE Communications Society Best Tutorial Paper Award, the 2017 GCN Best Paper Award, the 2015 IEEE Communications Society Best Tutorial Paper Award, Best Paper Awards of IEEE SPAWC 2007, and IEEE WRECOM 2007. And he was the recipient of an open fellowship for the EPR-SRC in 2022 and a consolidator grant by the European Research Council in 2016. He is the chair of the Signal Processing for Communications and Network Technical Committee of the IEEE Signal Processing Society and of the UK and Ireland chapter of the IEEE Information Theory Society. He is currently a distinguished lecturer of the IEEE Communications Society, and he was a distinguished lecturer of the IEEE Information Theory Society in 2017-2018. He's a fellow of the IET and EPR-SRC. So without further ado, welcome to Osvaldo Silva.
Okay, thanks, Irene. That was way too long. Sorry, I guess it was my fault. Well, thank you very much for having me. So in this talk, I'd like to discuss how to design AI machine learning tools for engineering, in particular for telecom engineering, given the theme of the workshop, in such a way that they can express their uncertainty. In such a way that they can know when they don't know. This is joint work with 2 members of my team at King's, Kfir Cohen and Sangu Park. Okay, so the motivation for this work is as follows. As I think we all know that machine learning models, for instance, neural networks, typically output not only a hard decision, for instance, the label attached to an image, but they also attach to this decision a confidence level, which is represented here by the height of these bars. So more precisely, a machine learning model outputs a probability distribution over all possible output values. And these bars, these probabilities, indicate how confident the model is in making a decision, or conversely, how uncertain it is in making a decision. Now, what is well known is that deep learning-based AI models tend, when they fail, and of course they must make mistakes more or less frequently, they tend to fail to make mistakes very confidently. So when they output the wrong decision, like in this case, the wrong label, they also attach to it a high bar, right? A high confidence level. And so we say that deep learning-based AI models provide poor estimates of their uncertainty, or more shortly, we say that they are poorly calibrated. Now, conversely, an AI model would be well calibrated if, in a sense, it would know what it knows and know when it doesn't know. So when making a decision, like in this case here, that is likely to be correct, the model also attaches to it a high confidence level, a high bar. Whereas when making a decision that is likely to be incorrect when tested, it also attaches to it a low confidence level. So it spreads out its uncertainty, right, across multiple output values, like in here. So again, the model knows what it knows in this case and knows when it doesn't know in this case. So the main premise of this talk is that calibration is a key requirement when AI models are used in engineering systems. And the reason is that AI models in such systems, let's say, for instance, this gray AI model, whatever it is, are actually used as part of decision-making processes, complex decision-making processes that involve other modules, maybe other users, even humans. And the importance, the performance of the model itself isn't so much in its input-output accuracy, but rather in the role they play in these decision-making processes. And for them to play a positive role, it's important that the other modules can trust the output of those models, right? Then calibration provides us with a way to ensure that this trustworthiness can be established, because this model, if it's well calibrated, it would be able to express to other models how certain or uncertain it is about the decision it's making. Now, I said that deep learning models are not typically well calibrated, and the reason is, to simplify it somewhat, is that they're not trained to be well calibrated, right? They're trained to maximize accuracy. And so this state of affairs calls to mind the quote by Alan Turing, who said that if a machine is expected to be infallible, it cannot also be intelligent. So the point here is that if we are interested in ensuring that these machine learning models can be trusted so they can quantify their uncertainty, we should design them in some sense with calibration in mind, right? And not consider calibration as an afterthought, right? As a thing we check on a model that we have already designed. And so in light of this, in this talk, I will provide kind of a review on the two main ways in which we can ensure calibration or can facilitate calibration in AI models. The first class of approaches changes the way these models are trained. And the second class of models fixes on a pre-existing pre-trained model and tries to calibrate it post-hoc after training. Okay, and for each one of these two categories of schemes, I'll very briefly give you a vignette of some work that has been going on in my group. But I'll start by providing a better definition or more precise definition about calibration of machine learning models. Okay, so as we said earlier, a machine learning model, let's say a neural network, takes some input X, depends on some parameters theta, right, the weights of this network, and then the output is a probability distribution over the possible output values of whatever output variable is of interest. So in this case, I have 4 possible values, and so this is a possible output of this model, a probability distribution over these 4 values. So we can use this output in the following ways. We can make a hard decision, specific decision. We can choose class 1 because it has the largest bar, the highest bar, the largest confidence. And we can also view this score, this probability, 40%, as the confidence level that the model has in this decision. And now we'll say that the model is well calibrated if it is true that for all decisions that have this level of confidence, let's say 40%, on average, the true probability of correct decision is indeed 40%. Right? So what we want is that these bars represent the true probability of that class being the correct one. So in that case, we say the model is well calibrated. So if we can trust these bars to be the truthful representation of the true probabilities, then we say the model is well calibrated. Now, calibration is a distinct requirement as compared to accuracy, and it's also a much more complex requirement to formalize and estimate. And this is an important topic for statisticians and machine learning experts to work on. The standard way to measure calibration is by means of a reliability diagram. So a reliability diagram looks like the one in this figure. So you plot the accuracy, the true accuracy of a decision in testing, right? Test accuracy versus the confidence that the model gives you. So the way you do this is you look at all decisions for which the model gives you some confidence, and then you evaluate the true accuracy of those decisions on average. Now, if accuracy equals confidence, so that means that the accuracy is on this dashed line, right, where accuracy equals confidence. So the model is perfectly calibrated. We can fully trust the confidence to represent accuracy. Whereas if the accuracy is above this line, then that means that the model is underconfident. The accuracy is higher than what the model predicts with its confidence. And when we are below, in this red line, the model is overconfident. So the accuracy is actually below the confidence that the model provides. So the model says you should trust this decision for 90, at the level of 90%, but the true accuracy is actually below 90%, and sometimes much below 90%. Okay, so as I said, deep learning models tend to be poorly calibrated. In particular, it turns out to be oftentimes overconfident. So This is, for instance, an example from a paper in my group where we calculate the reliability diagram, so accuracy versus confidence, for a demodulator of our fading channel. The blue bars you see here represent these lines here. The reason why we have bars and not a line is because we need to estimate the accuracy, and so we need to bin the confidence levels to be able to estimate the accuracy. So anyway, the blue bars, as you can see, are below this dashed line, and so that means the model is overconfident, right? So we cannot trust the confidence level that the model attaches to a decision. And this, by the way, is also true for the most modern machine learning models. For instance, this is the reliability diagram for GPT-4 in the OpenAI report. And as you can see, it's significantly overconfident. So these bars are below this line. So this is a problem across the board for many deep learning methods. And so there are two ways we can attack the problem. One is that we change the way in which we train the model. So we just train it differently in such a way that we target calibration. And the second class of schemes is that we don't change the way the model is trained, but after the fact, when we make decisions during inference time, we recalibrate the model in some way after training is done. Okay, so let me talk about these two classes and just give you some idea of work we have done in my group to address problems in these two categories of methods. Now, the gold standard for training-based calibration, I think you probably have heard this before, is Bayesian learning. So in Bayesian learning, what we do is we treat the model itself, so the weights of the model, as random variables. We make some prior assumptions about these random variables, we collect data, and we update our knowledge of the model, the best model to use, by updating this distribution over the models. So the distribution over the model parameters, which I represented in this figure with this, like marginal distributions for every weight. Okay, so again, by using the data we have and the model we make of the problem, we update this distribution, which represents our state of knowledge about the best model to use for our data. So this represents our state of epistemic uncertainty, so what we know. And the important thing to know is that the way we use this distribution over models, this distribution over weights, is through ensembling. So rather than making decisions using a single model, as it's done conventionally in machine learning, we instead use this distribution to generate several models, several neural networks. And now when we have to provide a decision for a certain input X, we don't run a single neural network, we run multiple neural networks, an ensemble of neural networks with the distribution we have discussed. And then we use the decisions of these multiple models to not only make a decision, but also to quantify the level of uncertainty we have. And to explain how this works, consider how weather prediction, weather forecasters quantify uncertainty. So in weather forecasting, what we do is we don't run, not me, forecasters, right? We don't run a single model, but rather we run an ensemble of models. And each model the models may disagree in their predictions, like in this case, quite different. Each member of the ensemble provides a different type of prediction, or they can generally agree on their prediction. So in the former case, when the models disagree, we can say that we can quantify, we can say that we have significant epistemic uncertainty, and so we can attach a high level of uncertainty to any decision we make. Whereas in the latter case, when the decisions are consistent, we can say we have a low level of uncertainty. Now, this distribution that we used for ensembling is not optimized, as we were saying earlier, to maximize accuracy, but rather is optimized by maximizing a different criterion, which is called free energy, which is really the sum of two terms. One term is really the accuracy or the loss, the training loss, conversely. And the second term is an information theoretic regularizer that takes into account how the distance between the distribution you're optimizing on, which I called Q, to a prior distribution. And in practice, solving this problem requires approximation like variational inference or Monte Carlo methods. I will not discuss this here, but there are ways to solve this problem in efficient ways or to approximate the solution in efficient ways. Now, let me show you one example of application of Bayesian learning to wireless system that we have looked at in some recent work. So here the problem is to design a digital twin platform for the control and monitoring of a wireless Internet of Things network. So we have a small wireless IoT network here where we have devices making correlated observations, and they need to convey them over a shared channel to a base station. And again, we want to build a digital twin, so a software platform at the edge or at the cloud for the purpose of controlling and monitoring the operation of the system. Okay. So what we do is, as we do it's typically done in digital twin systems, the digital twin builds a model of this physical twin of the network. And so this is a dynamic model that predicts how the network will perform. And so this digital twin, which is again a dynamic model, will contain modules that are selected based on domain knowledge. Maybe, for instance, we know how queues are updated, and other modules that are instead learned from data collected from this network. So this may be, for instance, channel statistics or things of this sort, or traffic statistics. Now, what we did in this work is we applied Bayesian learning for the training, the optimization of this model at the digital twin. So instead of working with a single model, a digital twin, so instead of putting all our eggs into one basket, so the digital twin trusts the model to be accurate, we use Bayesian learning. And so this allowed us to work with ensembles of models. So the digital twins will have an ensemble of models that represents the fact that there is still uncertainty on the true model that the digital twin should use for the physical twin. So it properly accounts for uncertainty. And we have used this model to implement several control and monitoring functionalities at the digital twin. And I guess across the board, what we found is that using a Bayesian approach provides much more robust and performant solutions as compared to a more conventional approach that uses a single model. For instance, we looked at the problem of using this model, this dynamic model at the digital twin to implement a model-based multi-agent reinforcement learning solution to optimize the policies that the agents should use. And again, we saw that using this Bayesian model is much more effective. And then we looked at other functionalities, like for instance, directed exploration, which means the digital twin optimizes the way in which the physical twin collects data. And we also looked at monitoring applications like prediction of outages or anomaly detection. So detecting whether the physical twin, the network, is behaving in ways that are anomalous, indicating that maybe there is a need to collect more data. Okay, and again, the main conclusion is that especially when we have limited data at the digital twin about the physical twin, it's very important that the digital twin preserves an understanding of its uncertainty about the model. Okay, so these are techniques that use Bayesian learning, kind of the gold standard, as I said, of training-based schemes. Now, these type of schemes have two drawbacks. The first drawback is that clearly Bayesian learning, as it's typically pointed out, increases computational complexity, right? We need to use ensembling, so multiple models during both training and inference. Okay. The second drawback is that despite all that, unless we are willing to make strong assumptions about how well specified the model we assume is in terms of prior and likelihood, we don't really get any finite sample guarantees that the model we get, the uncertainty estimates we get with Bayesian learning are well calibrated, right? So we don't get a guarantee that those bars are really trustworthy, right? And so post-hoc calibration schemes generally address the computational complexity challenge by operating on a pre-trained model, so not changing the way in which the model is trained. They can also be combined with Bayesian learning potentially. And there is a special class of such techniques called conformal prediction, which I'd like to focus on, that have formal guarantees of calibration. Okay, so provide guarantees that the model is well calibrated. Okay, so let me discuss first the class of techniques, post-hoc calibration techniques that you may have heard about. So this class includes, for instance, temperature scaling or isotonic regression or Platt scaling. They're very well known and used. The idea is extremely ambitious. So what these techniques try and do is take a probabilistic predictor like this one, which may be strongly overconfident, so really badly calibrated, and recalibrate it, so rescale, basically scale down in a way these bars, these confidence estimates, in order to make the model better calibrated. And the way they do so is by using a separate data set, a validation data set or a calibration data set, as it's called, in such a way, and they use this separate data set to ensure that the distributions they see at the output of this model match the distributions observed on this calibration or validation data set. And so this, again, typically entails scaling down these bars using methods like temperature scaling. Now, these techniques can be quite successful, but again, they don't address the issue that they don't provide any kind of theoretical guarantee of calibration. So for instance, they may just be overfitting the validation set if it is limited. So this is where conformal prediction comes in. So conformal prediction is in a way less ambitious than the schemes that I just described. So it is not trying to perfectly recalibrate all these bars. It's not trying to ensure that these bars represent true probabilities. That in fact can be proven to be impossible in a strong sense. What it tries to do instead is to take any probabilistic predictor, again, as overconfident as it may be, and convert it into a well-calibrated set predictor. And as I'll discuss in a second, a set predictor is in a way less informative than a probabilistic predictor, but it's still very useful. Okay, so how does a set predictor work? A set predictor takes an input X, and instead of producing as the output bars, one bar for every class, so assigning a score to every class, a probability distribution across the class, it simply says for each class, for each possible output, whether that output is plausible or not, right? So whether that output is potentially the true label, right? The true output or not. Okay, so the output of a set predictor is a set which contains a subset of labels that the predictor believes could include the true label. Okay, now this type of models again are less informative than a full probabilistic predictor, but they still provide a very nice and interpretable measure of uncertainty in the size of this set. For inputs that are easier to classify, you'll have a smaller set. For inputs that are more difficult to classify, you'll get a larger set. Okay, and so what conformal prediction tries to do is take a probabilistic predictor and convert it into a set predictor that is well calibrated. And by well calibrated, we mean the following. We mean that you set your preferred coverage target, let's say 90%. We call this 1 minus alpha. Then what conformal prediction allows you to claim is that the predicted set produced by the set predictor contains the true label with at least 1 minus alpha probability. So at least 90% probability. So this is the meaning of calibration for set predictors. They include the true label with a predetermined probability that you as a designer select. How does this work? Well, to explain it, let's make an idealistic assumption, which is not interesting, but is just for the purpose of argument. Let's assume that somehow we had a probabilistic predictor that is well calibrated. We don't, but let's assume we do, right? We can trust these bars to represent true probabilities. Now it would be straightforward to extract from this a set predictor that is well calibrated, right? For instance, let's say I want to obtain a coverage of 60%. So I want the true label to be in the set 60% of the time. If I trust these bars to be true probabilities, then of course I would just include class 1, which has probability 40%, and class 3, which has 30%. So that's 70%. It's more than 60%. And this is my predictive set. So one way to think about this is that we slide down a threshold or slide to the left threshold, and we include in the set the classes that correspond to the bars with the largest bars, right? The highest bars, until we reach the desired target probability, in this case, 60%. Now, of course, the procedure that I outlined cannot be used because we cannot trust the probabilistic predictor to be well calibrated. We cannot trust these bars to represent true probabilities. And so what conformal prediction does is to find this threshold using some side information. And so this side information can be either a validation set, like, or calibration set, like in the schemes that I described before. That's called offline conformal prediction, CP. Or it can be feedback from past decisions. So you make a decision, you decide a set, and then somebody tells you if that set included or not the true decision, and then you can adjust this threshold to meet the required coverage. And so let me give you an example of an application that we worked on of conformal prediction to wireless. This is the problem of proactively allocating resources for ultra-reliable, low-latency traffic. So the problem works like this. You have frames over time. Time goes down this way. And in each frame, you may have arrivals of packets of some traffic that needs to be served right away. These are these purple boxes. The problem is that when you're sitting at the frame, you don't know where packets will arrive in future frames. And you need to allocate these resources now because of latency constraints. So basically, you need to rely on a predictor that tells you whether in the next frame you'll get arrivals or not, and when you'll get such arrival. Now, the issue is that if the predictor you're using, if you trust the predictor you're using, and the predictor underestimates arrivals, then you will, of course, as a scheduler, allocate too few slots to this traffic, and the coverage level you'll get will be below your target. In this case, we had a target of 90%. If conversely, the predictor is too eager, overestimates arrivals, then if you trust it, you will just allocate too many slots, like these purple boxes, to this traffic, and then you will overshoot your target. So what we have done is to wrap conformal prediction around the very same predictor that we used here. And what we this way, of course, by theorem, you can meet the reliability target you set for yourself, in this case, 90%. And you can also do so without over-allocating resources. Another small contribution I wanted to highlight having to do with conformal prediction is the following problem. So conformal prediction, as I said, definitely ensures that the set that it produces as a prediction includes the true label with your target probability. But the issue is that this set may be very large. So in practice, it could be completely uninformative. Right? So at NeurIPS, last NeurIPS, what we presented is a way to try and minimize the size of this predicted set while still ensuring that they contain the true output with the target probability. And we did that by means of meta-learning. So we looked at several tasks, and we used that data from multiple tasks to come up with a procedure that then adapts to a new task whilst minimizing the size of the predicted set. And we have tested this on several benchmarks, including one on modulation classification. So here the problem is to distinguish modulation schemes on the basis of baseband signals. And we have seen that using conformal prediction with this method allows you to maintain validity, so maintain calibration, while reducing the size of the predicted set. Okay, so that takes me to the end. I hope I did not go too long. So the main point of this talk was to claim that if we want to use AI in engineering, oftentimes we shouldn't care only about accuracy, but we should also care about calibration. So we should ensure that the AI model is able to express its uncertainty. Particularly, it should be able to express when it doesn't know, so that other modules or users can trust the output of that module. And ensuring calibration calls for changes in the way we optimize these schemes, either at the level of training or at the level of post-hoc applications of the models themselves. In my group, we are also working on hardware solutions that can implement these schemes efficiently. And so there are, I think, many interesting directions for research. Maybe I'll just mention two. One is the interplay between calibration and privacy, as they both rely on randomization to some extent. And another one is the interplay between calibration and explainability. So we may be interested in using calibrated methods to explain, so using uncertainty quantification to explain decisions. But it's also interesting to think about how a model can explain why it has a certain level of uncertainty. Okay, so with that, I'll conclude, and happy to take questions. I'm not sure if anybody is still there, but yeah.
Maybe I'll ask quickly, could you comment on your paper on privacy and this trade-off that you just mentioned briefly?
Yeah, so I mean, I haven't, yeah, so the idea that I wanted, in particular, the paper that you're referring to that is cited underneath. So if you, as I said, Bayesian learning is the gold standard for training-based calibration. And what Bayesian learning does is at the level of at the test time, right? It requires ensembling. So it requires sampling from a distribution of models, right? And the same is true for privacy, right? If you want to disclose the weights of a model and preserve differential privacy, we need to add some level of noise, right? And so calibration and privacy, in some sense, so if you have a model that is well calibrated, so that applies ensembling, in some way it comes with privacy for free, right? Because by randomizing the choice of the model, one is also adding a level of privacy through randomization. In that particular paper that is listed down there, we use the idea of communicating the weights of a model over a wireless channel, which adds noise, and that noise plays two roles at the same time. On the one hand, it randomizes the output in a way that it allows us to implement some form of Bayesian sampling, Monte Carlo sampling, and on the other hand, the very same noise is useful to ensure a certain level of privacy. So it turns out that if you want to implement Bayesian learning in this fashion, some level of privacy comes for free, right? Just because of the fact that ensembling is inherently implemented by Bayesian learning.
Thank you. Thanks.
Any other questions?
To introduce our next speaker, who is Alejandro Ribeiro.
I see Navid has a question, probably, or not, or is it applause? Applause.
I will just, yes, thank you.
Thank you.
Yes, you can't find him.
I see Alejandro is the next speaker. Thank you, everyone.
Osvaldo, can you stop sharing? Thank you. Right. So to introduce Alejandro Ribeiro, Alejandro Ribeiro received the Bachelor's of Science degree in Electrical Engineering from the University de la República Oriental del Uruguay, Montevideo, Uruguay, in 1988, and the master's and PhD degrees in electrical engineering from the University of Minnesota, Minneapolis, USA in 2005 and 2007, respectively. He joined the University of Pennsylvania, Philadelphia, USA in 2008, where he's currently professor of electrical and systems engineering. His research interests include applications of statistical signal processing to the study of networks and networked phenomena, structured representations of networked data structures, graph signal processing, network optimization, robot teams, and network control. Dr. Ribeiro was the recipient of the Outstanding Research Award from Intel in 2019, 2014, Hugo Schuck Best Paper Award, and Paper Awards at ICASSP 2020, EU SIPCO 2019, CDC 2017, 2016 SSP Workshop, 2016 SAM Workshop, 2015 Asilomar Conference, ACC 2013, ICASSP 2006, and ICASSP 2005. So without further ado, I would like to introduce Alejandro Ribeiro.
Hello, so thank you for the invitation to speak here. So thanks a lot for the next 25 minutes of your time. So I want to talk about, I can't really see the video while I am presenting. So if there's any problems with the audio, please let me know. I am going to talk today about my work on autonomous wireless communications networks. So let me motivate the kind of problem that I am trying to study. Not that I am trying, the kind of problem that I study. Period. So here we have this notion of an autonomous wireless network, which is trying to support communications of an autonomous team. So here you have a set of red dots that are appearing and disappearing. And they disappear when they get out of communication range from the network. And this network is being maintained here by these three blue agents that are repositioning themselves to enable the presence of this communication network. In this next motivating problem, the setup is that we have a team of drones that want to execute a certain task, or that could be generically a team of robots that want to execute a certain task. These robots, in this particular case, they're consensing, that all of them trying to fly at the same velocity without colliding with each other. And in order to do that, they need to communicate. Now, in both of these cases, you can see that, okay, there's some cyber physical, there's some physical task that has to be accomplished, but there's also the need to establish a communications network that will support whatever task it is that this autonomous team is trying to execute. These are the motivating examples, and in both of these examples, there's some machine learning involved in order to solve the task of interest. There's a CNN in the first one, there's a graph neural network or GNN in the second one. But what I want to talk about today is not about how we solve the physical task, but how we solve the communication task. More to the point, right? This is the abstraction that I want to consider today. We have teams of agents forming a wireless communications network. That is, they're communicating over a shared wireless medium. And our goal is to allocate resources over this graph so that agents can communicate with each other according to a certain quality of service required. It is, of course, very important for me to point out that the interference that characterizes this wireless network is something that is well described by it goes perhaps without saying that these are problems that are difficult to solve. I started doing optimal design of wireless networks in 2003 when I started doing my PhD. It's been 20 years, and we've made progress on these problems, but they continue to be challenged. And the reason for that is not unknown, is that these are computationally intractable problems in the sense that finding the optimal configuration of the network is intractable. Except in those cases in which you have a small number of agents. And actually we know more about that, is that these problems become intractable because of the fact that information is partial. Agents only know the local network, but their goals are global. And that tension between having access to information for me to make my optimal decisions when the goal of the network as a whole is global is what creates this computational intractability. Now, if the problems are intractable, well, that motivates the use of heuristics, okay? And in particular, given that we are in the year 2023, why not consider learned heuristic? That is, instead of being a heuristic designed by a human engineer, it is a heuristic that we learn from the data, which, by the way, would also have the advantage of being applicable when models are unknown, although I'm not going to be talking about a particular problem. They are, however, well, by the way, I mean, once we reach this point, we could say, fine, let's call the machine learning engineer and forget about the problem. But actually, no, we cannot do that because these are not standard machine learning problems. These are unusual machine learning problems. And I think that they are unusual in two ways. The first way is that these are problems in which constraints play a critical role. Typically in machine learning, we say, let's minimize a loss. Let's minimize a loss subject to fairness, perhaps, or subject to robustness, but it's not much more complicated than that. Here, however, it's not a loss that we're trying to minimize. It's a resource that we're trying to administer, a resource that we are trying to allocate. So that makes the optimization problem different. It makes it an optimization problem in which constraints play a central role. A second reason why these problems are different is because we want to make them scalable. Unusual, sorry, is because we want to make them scalable. We're not trying to allocate a point-to-point channel. We're trying to allocate a whole communication flow. I'm going to show in this talk the following things. With regards to constraint learning, it could be that in principle, learning with constraints is fundamentally more difficult than learning without constraints. In the case of scalability to large networks, the challenge that we face is that the scalable techniques that we have for machine learning work on Euclidean signals. In the case of learning with constraints, the result that I will show today is that, in fact, even though learning with constraints could be much more difficult, it is at the end of the day just as difficult as learning without constraints. And the precise statement of what this means will become clear later. In the case of scalability, what I will present in this talk or discuss in this talk is how to generalize convolutions to signals supported on graphs so that we can operate them to attain scalable learning overlaps. And let me therefore begin with the first part, in which I'm going to be trying to explain what I mean by allocating constraints. And for that reason, let me talk about the problem of optimal resource allocation in wireless communications. That doesn't necessarily have to be wireless network. So let me explain. You know, the determinant characteristic, we all know this in this audience of a communication channel, is the received signal strength. Right, so we put some power into the channel. At the output, we have, you know, the multiplication of the channel times the input plus noise. So this, ratio of received signal strength to noise, that's what determines the characteristic of the channel. There are several metrics that the RSSI controls, but let's just focus on one. Let's say that we are interested in maximizing communication right here. So, you know, given the channel H, we allocate a certain amount of power P. At the other side, we receive power HP. Let's say that we're using capacity achieving codes just to, you know, just to fix ideas. And the rate that we're taking here is the log of 1 plus HP. Now that's, you know, elementary. However, what we do know is that in wireless communications, the channel strength changes over time, which means that at some point we're going to be experiencing deep phase, such that no matter how much power we put into the channel, it is impossible for us to get this communication across. But at some other points in time, we're going to be experiencing a positive fade, or a good fade, let's say. The opposite of a fade, I should say, to be more precise. In those instances in time, that's when we would like to communicate. That's when we want to transfer. What I mean, therefore, is that we don't have just a single resource allocation problems. We have a resource allocation problems over a random realization of a fading state. So that is, we are going to consider an adaptation of the power to the actual state. Sorry, an adaptation of the power to the actual state of the channel. And instead of optimizing instantaneously, we would optimize over the long run. So that's why I have, like, you know, this family of channel realizations. Now, okay, now maximizing this quantity is not that interesting. Just blast as much power as you want, but of course, blasting as much power as you can. However, blasting as much power as you can would deplete your battery, which means that in general, that's not the problem that we want to solve. We want to solve a problem of this form, in which we want to maximize our respective communications rates subject to a power constraint required, right? Or subject to a power budget. Or, you know, maybe we want to do the opposite. Maybe we want to minimize the expected power subject to a rate constraint. Just to make, you know, these two problems unified, let me introduce a little bit of rotation here. Let me introduce a general utility of the rate and the power. The rate is given by this expectation. The power is given by this other expectation. And, you know, that's like a generic way of writing these optimization problems in wireless communications. What I want to emphasize is that when you look at this problem, this is an unsupervised statistical learning problems which, however, differs from a standard statistical learning problem in that the statistical losses appear as constraints. This is, I think, an interesting observation because we sometimes think of wireless communications as an area where machine learning can be used, but actually it's not that. I mean, the allocation of resources in a wireless communications system is inherently a machine learning problem. We are calling H fading. We are calling P of H a resource allocation. We are calling R a rate. But I could call H a feature, P of H an output feature, and R I could call it loss. I could call it a loss. If I do that, that's the language that we use in machine learning. So mathematically speaking, the problem of regression in machine learning and the problem of allocating resources in wireless communications are identical, except for the fact that in wireless communications, we just don't want to maximize some losses. We want to balance a number of requirements. Now, this is not yet in the language of machine learning. To put this more into the language of machine learning, I need to introduce the learning parameterization, right? So we don't solve these problems natively in machine learning. We introduce a parameterization A, and instead of learning the P of H directly, we want to learn the parameter. To give you a more interesting example of what I am talking about here, right? So suppose that we consider this wireless communications network, and suppose that this is an interference limited wireless communications network. So I am writing down the instantaneous SINR. So that's the performance that I attain at a particular point in time. If I now consider the long-term average, each individual agent I is attaining a particular rate I, and each agent I has some power budget that limits their communications, and we maximize the utility of all of the rates and powers. But I want you to observe, right, that when I go from a wireless channel, point-to-point channel, into a wireless network, the constraints now become much more difficult because I have like a large number of constraints, and not only that, I have a large number of variables here that need to be decided. Now, the problem, of course, needs to be parameterized. Therefore, I'm going to introduce this parameterization A, which controls the allocation of resources. And just to avoid writing a sophisticated problem or a cumbersome problem like this one, I should say, I'm going to adopt the notation that all of these constraints are just write them as the expectation of a certain vector function f, and subject to, with the goal of maximizing a utility u of x when x is given by that expectation. Now, these problems are challenging, as I told you before, and they are challenging because both f, the function f, and the parameterization A are not convex. Okay, and being not convex, it prevents us from operating in the dual domain. And operating in the dual domain, that's how and when optimization problems become. Now, in order to but let me set the problem aside for a minute, and let me say, okay, fine. And when I go into the dual domain, I lose optimality, but let me go into the dual domain anyways and see what happens. Going into the dual domain means that for each of these constraints, you're going to introduce a Lagrange multiplier, and you're therefore going to write down this Lagrangian, where you have the objective u of x plus lambda transpose e is expected value of these vector functions that depend on the channel, the resource allocation, which depends on the parameterization and the channels. Now, we are in familiar territory now, because that's the advantage that the Lagrangian has, which is that maximizing the Lagrangian. Now, that's an unconstrained learning problem, you see? Remember that I told you before that in principle, this problem of working with constraints and without constraints are very different. Why are they very different? Well, because we don't have duality. If we have duality, then constrained learning and unconstrained learning are roughly equivalent, because you can always get a problem with constraints and transform it into a problem without constraints through the Lagrangian. But unfortunately, there's duality gap here. So there's something that we are losing. What I mean, to be more precise, is this. I mean, we define this function g of lambda, which is a number or a family of approximations for different lambdas. But which of the lambdas should we use here? Where we should use the lambda that makes the primal and the dual problems as close as possible. But the challenge here is that in principle, there's no any meaningful relationship to be. Now, the fact that I am highlighting this so much, it should lead you to the correct belief that in the end, this will work out. And actually, this is, work that we did in 2019 with Mark Eisen and some other of my collaborators, which demonstrated that even though these problems are not convex, they still have a small duality gap. To have this small duality gap, we don't really have any conditions other than requiring the parameterization to be near universal. But for as long as the parameterization is near universal, we're going to have a duality gap of order epsilon. Here, what appears as a determinant quantity is the one norm of the optimal Lagrange multiplier. And this really is something that you would expect to appear because this Lagrange multiplier is controlling the sensitivity of the optimization problem, and statistical approximation is essentially a problem of sensitivity. Now, having proved that these optimization problems have a small duality gap, we can now propose an algorithm that will more or less solve this optimization, this learning problem in wireless. This algorithm is a primal dual algorithm in which we have a gradient descent step in the primal domain, followed by a gradient ascent step in the dual domain. And for as long as you have duality gap that is close to zero, this algorithm is going to converge. And that's what I wanted to say about the first challenge of wireless communication. So let me perhaps recap a little bit of the concept that I have been trying to get across. The first concept that I try to get across here is that, machine learning is a way of designing heuristics for the allocations of resources in wireless communications. That's how I see it, and I think that that's a valuable way of looking at the problem because it tells you that it's not that different from what we have been doing before. Ideally, we have these optimization problems. We want to solve them, but they're intractable. Given that they are intractable, we have been using our brains to try and come up with these heuristics. The idea in machine learning is to do not really utilize our brains to come up with heuristics, but utilize our data. Of course, data is not a good substitute for a brain. I think that's a very fair thing to say. You could consider a candidate for my epitaph. Why is data not just a plain substitute for a brain? Well, because, problems have their inherent properties, and it behooves us as systems engineers to leverage what we know of our systems to decide better machine learning algorithms. In particular, in the case of wireless communications, I think that there are two challenges that require the actual use of our brains. The first one is that we have machine learning problems with constraints. The second one is that we have machine learning problems with graph structure. Both of these requires that the first one that we consider how to learn with constraints, and the second one that we consider how to learn with graphs. I discussed how to learn with constraints. The answer is actually very simple in the end. We moved into the dual domain and we learn as if we were learning without constraints. But it is critical that in that movement from the primal to the dual domain, we show that this can be done without loss of optimality. Otherwise, you begin with this optimization problem, and before designing your learn heuristic, you're already losing optimality. But no, you're not. I mean, we can move into the dual domain without loss of optimality. I want to talk now 5 minutes, perhaps, about learning at a scale with graph neural networks. I mean, the challenge, the second challenge is something like this. I mean, I have, I believe, 50 or 100 nodes in this network. So we want to operate in networks with hundreds of nodes. Machine learning is not inherently scalable, right? Something like a fully connected neural network does not scale well. The neural networks that we know scale well are convolutionals, but convolutional neural networks apply to Euclidean signals. What I mean is summarized in this picture. If you give me something like this, I know how to make machine learning scalable. if you give me something like this, well, by now it's becoming known, by the way. I mean, graph neural networks are quite popular by now, but in principle, you know, attaining scalability on this network, on this data structure is very different from attaining scalability on this regular grid. But the trick is this. When we look at time or space, convolution, that is the standard convolution that we utilize, they are operations on graphs. Because that's what a convolution does. I mean, you get your local data, you multiply by a certain coefficient H0. You get the data of your neighbors, multiply by a certain coefficient A1. You get data of two hop neighbors, you multiply that by a coefficient H2. You know, and you keep doing it. If you want to define convolutions on graphs, well, change the graph, but do not change the operation. You know, you begin by considering your local data, you scale that by a certain coefficient A0. You get the data of your neighbors, which you scale by a coefficient A1. The data of your two hop neighbors that you scale by a coefficient H2. The data of your three hop neighbors, which you scale by a coefficient A3, and so on. I know that if you have seen neural networks before, this looks like a different way of defining graph neural networks. It is a different way, but it is equivalent. And I like it because it makes the connection with the standard convolutions obvious. It's algebraically the same operation. It's just that we change the graph on which we are working. So, you know, if you know any representation theory, what this means is that algebraically it's the same object. We are changing the instantiation, or we are changing the representation of the object depending on the graph. Now that's a graph convolution. A graph neural network is actually a very simple extension of a graph convolution. You get a composition of a cascade of layers, each of which is itself the composition of a convolutional filter with a pointwise nonlinearity. And in each of these layers, you have a set of coefficients that you need to learn. That's what we call the filter tensor A, which is the learnable quantity that we will throw out, learning parameterization. Observe something very remarkable here, which is that in this architecture, the output depends on the filter tensor, that's the quantity that we are learning, on the input signal X, but it also depends on the graph. Okay, and this is very important because when we consider wireless networks, this graph is changing. Right? It's changing over time, it's changing from realization to realization. It may even change because maybe we decide to train on networks with 100 nodes, but tomorrow you give me a network with 200 nodes. So there's some intriguing question here of what happens with the output of the GNN as S changes. And I'm going to give you some interesting results on that. Now, before I discuss that in more detail, the first thing that I want to show you is that this idea of a scaling with graph neural networks does work. On the graph on the left, I am showing the performance of some heuristics, some bad heuristics like a random selection or equal power. A good heuristic, which is MLSys, which I am certain some of you have heard of before. It's a very it's a widely used and very clever algorithm, I would say. And here in green, we have the train performance of a graph there's a typo here. This is the train performance of a graph neural network, and this is the train performance of a fully connected neural network. And you can see here that both of them, the fully connected neural network and the graph neural network, eventually they both learn something that actually is better than WMMSE. The GNN learns something that looks a little better, to be honest, to be fair, perhaps. But, you know, not that much better, to be honest. It does learn way more quickly, right? So instead of taking, in the order of 15,000 iterations to converge, it takes in the order of 2,000 iterations to find a good learned heuristic. What I am not telling you yet is that this is in a network with 20 pairs. Suppose now that you want to solve the same resource allocation problem in a network with 50 pairs. Well, now the situation becomes very different because there's no fully connected neural network in this plot because the fully connected neural network, we couldn't get it to converge because the training took too long. But the graph neural network still learns how. Here I have what I think is a more intriguing experiment, which is a transferability experiment. So what we're doing here is this. We are training in a network with 50 agents, but then we start executing the train GNN on networks with larger number of agents, 100, 150, all the way up to 500. And observe here how the GNN continues to deliver good performance, even though it is not retrained on these larger graphs. So that's the property that we call transferability, which by now we have verified empirically in several settings. And we also have some theoretical analysis that justify that this is indeed the case. Now, this is the bulk of what I wanted to say. I wanted to tell you that machine learning in wireless communications, to my mind, is a very well justified approach because it's a way of building heuristics, building learned heuristics as opposed to heuristics designed by engineers. However, it's not just, okay, let's apply machine learning and forget about it. No, these are machine learning problems of a different nature, and therefore they require different approaches, in particular because we are dealing with constraints and because in order for them to scale, we require the use of a scalable architecture, which I am proposing the use of. I want to close by highlighting very briefly a couple of more recent works. I told you that there's a bunch of constraints that you want to satisfy. Okay, satisfying constraints is easier said than done. It is sometimes difficult to find a specification that is feasible. To overcome that problem, we have developed this concept of resilient learning, or this concept of resilient resource allocation in wireless networks, in which we devise a way of relaxing constraints on a manner that is proportional to the sensitivity of the optimization problem to the relaxation, which is a way of saying that we are relaxing more difficult constraints by larger amounts. And a second problem, which is detail, very important detail, however, that I did not highlight about primal dual problems, is that primal dual learning problems do not necessarily converge, but they converge on average. That makes their transference between training and testing, training and operation impossible. And that's a problem that we can overcome by the introduction of a state augmentation algorithms. So this is something that we developed in this paper. And both of these papers, by the way, are mainly the work of Navid Naderi Alizadeh, who was in my group, but who is one of the co-organizers of the workshop, and that has really been pushing the envelope of machine learning in wireless here at the University of Mexico. This is all I had to say. I mean, I just have here some concluding remarks. So learning resource allocations in wireless communications requires that we learn with constraints. And it also requires that we scale to large networks. In principle, learning with constraints is fundamentally more difficult. In the end, it's not. It's just as difficult. Scalability is an issue because we don't really know. We are not as versant scaling on graphs as we are scaling on grids or scaling on time. But that is a problem that we can overcome by generalizing convolutions to graphs and developing graph convolutional. This is all I have, so thanks for listening, and I will be happy to take any questions if you want to ask. Thank you. I think you are muted, Erwin.
Oh, can you hear me? Hello? Test, test.
I hear you now.
Yes, a great presentation, Dr. Ribeiro. I was asking the audience if they had any questions or if there's questions on Zoom. Okay, so I don't see any questions. Thanks again for speaking. A great presentation. So currently we have our 10-minute break. We reconvene at 10:45, and then we have the speaker, Dr. Tara Javidi, at 10:45 to 11:15. All right, great. I'll be back in 10 minutes.
Thank you, everyone. I hope that you're having fun. Bye.
No computer, should I just log in?
Zoom?
Uh-huh.
You're going to present on your laptop using Zoom?
Yeah, that's easy, right? And what I will do is maybe keep my audio off.
Okay.
That way it doesn't have any, and then I'll just do this.
It's like the
No, I
projector.
don't want to do that. Yeah, exactly. Maybe I'll just do this. Good. I'll be looking. Yeah. Okay. That's
the tech support people, see if they could.
No, this is good.
Okay.
This is easy.
Okay. Well, best of luck.
No, it's just good. It's just that because it doesn't. Yeah, maybe. Switch in terms of which one would be on top, which one goes down.
Yeah, we could.
You know what? No, I'll just be. I think that's good. These are all locked. It's better. Okay. Just, yeah, and that way.
I could look for another table possibly something higher up for you.
Yeah, it's okay. It's just that, when I do it, because it doesn't. Maybe that's fine.
Wait until 10:45. So
But that's fine. For everything to read, but when I come back. Okay. Yeah, they want it. Yeah, as long as they want. Yeah, okay. Okay. Mine is sure. Especially on all the, like, every single thing.
All right. Welcome back to the workshop on resource-constrained learning and wireless networks. Up next, we have our speaker, Dr. Javidi, and I will start a introduction. So, Tara Javidi received the Bachelor's of Science degree in Electrical Engineering from the Sharif University of Technology from Tehran, Iran, the Master's degree in Electrical Engineering Systems and Applied Mathematics, Stochastic Analysis from the University of Michigan at Ann Arbor, and the PhD degree in Electrical Engineering and Computer Science from the University of Michigan at Ann Arbor in 2002. She is a Jacobs Family Scholar, a Jalisco Data Science Fellow, and a professor of electrical and computer engineering with the University of California at San Diego. She is the editor-in-chief of IEEE Journal on Selected Areas in Information Theory in 2022 to 2024. So without further ado, I would like to introduce Dr. Javidi.
Thank you. I want to thank the organizers for inviting me. It's been a long journey to finally be attending this workshop, so it's good to be here. So I'm going to mostly talk about work that I've been doing as part of the AI Institute, the TILOS, standing for the AI-enabled learning and optimization for at scale. Okay, so This is an NSF institute, and actually Alejandro, who spoke before me, is another faculty member involved. And so the work that I'm doing there is the summary. Okay, so we wrote this proposal. We were talking about how AI has had major sort of success in terms of revolutionizing the way we live, and in some sense, learning neural networks from data has sort of revolutionized the way we think of engineering. And the proposal and the aim of this NSF AI Institute has been to expand this success in more realm of engineering, and in particular, we thought optimization of systems that are both physically constrained and at the same time are, the scale of them is large. So you really need to rethink the way we have designed these systems. And in particular, so in parallel to foundation works on AI-enabled optimization, we have groups that are working on particular application areas, and I'm leading, co-leading, in fact, with Alejandro, the work we are doing in wireless networks. And we thought this is a fantastic engineering application as a good match for this kind of AI-enabled optimization. So I'm sure everybody in this room and on Zoom, in fact, interested in this topic, has done ML applied to many areas, and this is sort of my own portfolio. But as I said, for this talk, I'm going to focus on the specifics that we are considering under the auspices of TLOS. So this is the slide, the presentation that we made to NSF when before we got it. And there we argued that wireless networks are a very good example to test how well you do on optimization front for various reasons. Because first of all, with the fact that there are infrastructures of the world, of the information in the world, they have scaled to be so large that really they will push optimization methods to their limit in terms of scale, as well as they're very limited on their physical constraints, both in terms of where you put access points and where do you actually deploy them as an infrastructure, but also in terms of the physical, the physics of electromagnetic fields that actually carry this information. So we really thought about, we really need to think about optimization at a different scale, and we propose very many applications, but I'm going to focus on one that here is in that photo on the right. Maybe a more animated version is in case of disaster risk, recovery. You will have this infrastructure that has enabled you in a hospital and home for healthcare that will go down the sort of the stationary infrastructure, and in the recovery you would like to convey the same amount of information, help, maybe even for more critical care provided to mobile devices that are now going to be deployed. And so if you think about it, you really have to think about how do you optimize these networks, right, on the go and in situations like this. I will come back to this application later when I'm talking about decentralized control for wireless. Okay, so broadly, I've been thinking, how can I get rid of that Navid's name on the screen? It's distracting me. I'm sure everybody else is okay with it. Perfect, thank you. So broadly, the formulation that I have come up with, and everything today I'm going to talk about goes back to this, is something like this. When we think about deploying a wireless system, we do a lot of pre-processing, thinking about how we're going to run these, we design our protocols and so on and so forth. We put the infrastructure in place. And then associated with with that infrastructure, we have a lot of free parameters. They could be protocol parameters. They could be physical parameters, such as how do I actually, sort of put my antenna array, and where do I put them? So from physical parameters that are in your design control to software parameters, protocol parameters, these things, you can sort of think about them, will all affect network performance, be it latency, reliability, connectivity, power. But unfortunately, the scale of the network is so big that it's impossible to imagine I have a clear understanding how setting these millions of parameters will affect my network performance as a function. So this function is now a black box in some sense, that is the network. How do we normally do it? Even this is even like in the 90s or early 2000, when people come to a building and set, for example, your wireless devices. You can imagine a very similar setting. They put the infrastructure points. They have some software control over how to set this up, and they let it run. They wish for the best. They let it run. You complain as a user of that building if there is a coverage issue. They monitor it for a long time for power and other constraints that they have, performance metrics that they have in mind, and then they come back, renew all of these decisions that they made, right? So you can sort of think about it empirically optimizing. Right? So the function is not known to me, but I have to empirically optimize it. And of course, I picked this example because every experiment that you run is very costly, and at the same time, the system is running. So it's an empirical scenario where sampling your function is incredibly expensive. Now, the second aspect is that you might be making the decisions in completely decentralized way. So when you do enterprise decisions according for Wi-Fi cards, maybe you'll do it all centrally. But now if you want to scale this up to a larger metropolitan area, now different designers are doing this in a distributed fashion, right? So the two sub-problems that we have looked at are the empirical black box optimization. I'll tell you, this is basically saying I have a function, I can measure the value of this function on particular instances, and I would like to optimize it with few experiments, with few measurements. Maybe I have some noise. So this is very popular in machine learning literature under the auspices of black box optimization or Bayesian optimization, and it's used to decide on hyperparameters before you do decide to train a neural network. So it's gaining a lot of popularity, and we wanted to sort of apply those methods in wireless setting. And if I have time, I'll talk about our results in that space. The second one, which is the first topic I want to talk about, is decentralized control and optimization in these systems, right? So there are two aspects. The one is this empirical fact. The second one is that we would like to do in a decentralized way. And this touches upon some of the stuff that Heiji talked about at the beginning of the session on sort of extensions of federated learning to the wireless system operation. I forgot to mention, all of these work are done by my PhD students. The colors are associated with the two topics that they're talking about. The students whose names are in black are previous students whose early foundational work has contributed to what I'm going to present. So I felt like I should put their name. And this is all joint work with my colleague Farina Sushan. So let me talk about decentralized control and learning. So again, here, let me go a little bit deeper into the setting. So the problem of decentralized control is actually pretty well studied from a long time ago. And the idea is that you have a plant model, and basically you would like in a distributed fashion, you have sensors that are making local observations, X1, X2, and so on. And they would like to work together cooperatively to control the plant according to some objective function. So the goal is one thing, they're all teaming up and they would like to do it in a decentralized fashion, right? And you can think of, depending on the application, you can say, I'm going to minimize the cost or maximize the reward. They're interchangeable, so I could use. So here, what we are interested in, what happens if this plant model, the dynamics, is not known to the controllers, right? So now embedded in this control problem, there is a problem of learning. And because they're decentralized, there's a very natural extension of federated learning, as you can imagine. This is joint work with my students Shinkan and Anusha. So let me just look at a simplest setting, just for the purposes of the talk, and so that it's easier to talk about the problem, and it would be easier. So the easiest control problem you can put in this context is, I have basically two agents. They observe X1 and X2, two subsets of your state variables. And these state variables are run according to an unknown dynamic A star and unknown response to the control B star. So A star and B star are dictated by the reality of the world, but is unknown to the controllers, and some noise model. Again, here in this, it's useful to think about W1, W2 as Gaussian noise. But really, for everything I say, it's irrelevant, but they're statistics. Now, the peculiar thing is that the cost function here is a joint cost function for both of them. So while they're observing locally and they're exerting control locally, their cost is a joint cost, which consists of what happens to the full state of the system and how their decisions line up. And they are interested in minimizing their cost. And since they don't know the system, we say they are interested in minimizing their regret relative to a genie that would have known the dynamics of the system. Okay? So you might say, oh, this is very esoteric. Does it ever come up in wireless systems? And yes, indeed, the problem that Alejandro was showing you the video, this autonomous wireless setting, in fact, is a very good, is very well captured by this. So let's say you have a couple, you are dealing with this sort of a delivery of care in a disaster, post-disaster. So you want to imitate the the wireless infrastructure in the time where your cell tower has fallen out of function. So you have UAVs and drones that are basically, the way we think of the architecture is that UAVs play like a mobile infrastructure. They will actually guide the drones to how to best increase the coverage. So while each UAV might be responsible to control its own drone, its own microcell, as you can imagine, they will interact with each other, they will interfere with each other. So their goals are very much, the costs are very much aligned. So in this setting, for example, the locations of the drones will be subject to their movement, as well as actually the movement of the larger UAVs. And those movements are out of our control in some sense. The dynamic comes from the dynamic of how well you can position these drones, with what inertia you can move them, but also subject to noise, perturbations such as the wind and so on. So you would like to align them. The interesting thing here is to notice that even in the scenarios like I've drawn, where everything is distributed. So in that model A star, the model dynamic, here I have a very localized, it's almost clear that I will have a block diagonal dynamic A star in this setting. If I don't have a federation of communicating between these drones, I can easily mess up and cause more interference on the ground than I should have done, right? So it's very clear that I would need to improve on the learning here and joint learning. So back to the simplest setting. So what happens here is, as I said, you would like to compare yourself with a user that would have known all the dynamic and would have just told these, controllers to do exactly what to do. Now, it turns out that if I knew the dynamic, even though the problem is a decentralized problem, what we could have done is if the dynamics was known to the controllers, each of them can take a copy of the dynamics, run a Riccati equation, solve it, get the optimal controller gain. Here's this matrix. And now each of them can really do the best for themselves as well as for their cooperator controller. So in other words, the regret for a decentralized controller, for decentralized controllers that know the plant dynamic is 0. So that's kind of good news for those of us who have done federated learning, because this really says if you do, in fact, solve the problem of collaboratively learning the dynamics, then really the rest of it is in the wash. Then the rest of it can be done pretty much by solving computationally what needs to happen. So here is our algorithm. It's a lot of details, but let me just give you each. There's a warm-up period for them to sync up what they want to know. And then there is a local learning, which basically involves system IDing, figuring out my local dynamics. There is a federated learning component where they talk to each other and they sync up their knowledge across, and then do an adaptive control, applying pretty much as if the network, they know the truth, they do the optimal thing, and then they talk again to each other to recalibrate their knowledge. So they do this I could give the theoretical result, but I think this is more telling. So here I have two controllers. I basically have a close to diagonal dynamics and influence of each of the decision maker, each of the UAVs, only affecting their own drone decisions. But again, remember that they have to collaborate because the cost is a joint cost. And it turns out that what you would get, and this is what we're showing simulating our performance, is that the regret of doing this sort of separated, first do local learning, then do federated learning, and then do control, will give you a regret that scales square root of t, which we know even in centralized setting, that's the best. So in some sense here, this is a proof of concept that this federated learning box really solves our problem for solving this problem. So how am I doing on time? 15 minutes maybe. Yeah, okay. Yeah, so in what I was just presenting, the most important building block is the ability of the two drones to jointly learn something. And this is sort of foundations of federated learning. However, unlike federated learning that we're used to, federated learning, you basically have devices that are experiencing some data and they would like to pull it together to learn a better model for all of them. The comparison is really with federated learners that are dealing with incredibly different data sets. So this is called non-IID challenge in federated learning. And we know that many federated learning algorithms do poorly when your data is this partitioned. Now, in my problem, these are control problems in the distributed control. Their physical realities are very different, as Heiji was talking about. So the physical reality means the perturbations they're seeing, as well as the dynamics, are going to be different. I have one drone that most probably is expensive, is bigger, it can tolerate wind a lot better, and another drone that maybe is cheaper, or has been damaged. So the dynamics of these systems are very different. So you will see data that are very, very different. So what I'm showing you is the non-IID challenge posed for federated learning, where you're just doing simple vision tasks on images collected across the world, and that geography being different. But imagine how much this will be, and you can easily see the performance degradation for much of the algorithms in the literature. But now imagine that I'm dealing with these control systems where the non-IID-ness is even in my control. I basically, what I do affects what I will see. So not only I have non-IID behavior caused by the world being different, but also by what I do. So here, the name of the game for us have been to really think about these problems in a Bayesian setting, as I believe Oswaldo was talking about. Really think about learning not only one model, but learning ensembles of models. So really our federated learning framework is really dealing with uncertainty and exchanging uncertainty as well as decisions. And this is old work, so I'm not going to go too deeply about it, but I would just say that just like in federated learning, we're going to do moments of communicating models and then merging models. But because in many control applications, you're dealing with graph structures and not this sort of a simple star topology, we had to adapt it to also work on peer-to-peer in a peer-to-peer fashion. So at every time, each agent starts with some uncertainty model and basically draw samples. Based on the samples, they refine their model. And again, think about their models both in terms of uncertainty and the mean model. So here we tend to think of it as a belief. You could simplify it, as I will show, in terms of mean and variance, but in general, it's a belief that you compute locally, and then these beliefs are disseminated across the neighborhoods across each agent, and then basically these public beliefs are gathered, combined, merged together, and this is what I discussed in the previous topic, which was the control. So they merge this, and now they have a common knowledge in their neighborhood of what is happening. And the interesting thing is that if you let this run, essentially you converge to the truth, to finding that theta star. For us, it was the sort of model of the dynamical system that you're trying to control. And this convergence results goes like this. This is again a simple setting. If you work on a star topology, in my setting, if you think about it, it was a really simple linear system with Gaussian noise and quadratic cost. So in that setting, I'm just really learning, I'm regressing on some linear model, right? So it's just distributed or decentralized linear regression. So here is a model. So I have a central node that is connected to everybody. You can sort of think about that as the larger UAV, and the other ones that are the smaller UAVs, and they're kind of learning their own models. But because you're interested in really controlling in all scenarios, you're kind of interested in learning this larger model because, as I said, the controllers have to each know what is happening in order to line up their behavior for a better cost. So here is what the performance looks like if the essential agent was in charge, so they were not distributed, decentralized. You would learn the MLSys of finding the optimal weights. The optimal model is shown in the black. And if they were not communicating, if they're not federating the learning, you will see that given their location, some of them are orthogonal to some dynamics of the system. They will not learn, but if they communicate, they learn almost with the same speed that the central learner does. Of course, what I just showed you is a simple setting when you're really doing linear regression. If you think about it, in my setting, I am deviating. I'm in the non-realizable setting, because even though my observations are impacted by some true physical system, it's also impacted what my neighbor is doing. So I'm approximating my neighbor's behavior as a non-realizable deviation from the truth, and it turns out that our results extend nicely. Now, everything I talked about was for linear regression. I posed the problem as an unknown plant that you don't know anything about it. I simplified looking at the linear setting to explain the ideas, but it turns out the extension to decentralized variational learning is also possible using Bayesian neural networks. So the key concept, and I think Oswaldo did a great job, is to think about looking at an ensemble of neural networks. So they have similar architecture, as I've shown here, but the weights can come from sort of a distribution. Right? In a variational setting, instead of working with all ensembles as all possibilities, we make a simplification and look at simplifying assumptions. So for example, a very common one is that you assume the weights come as Gaussians with a mean and the variance. Okay, so this simplifies quite a bit. You now don't need to create an ensemble of many neural nets. All you have to do is keep one neural net with the mean behavior and understanding of what the variances at each edge can be. And of course, the larger the variance, that means that edge has more ensemble of possibilities that allows you, and hence the output of that, the output going from the outgoing nodes is more subject to uncertainty. So you take these models and you apply the exact same framework of federated learning to these neural nets using this variational trick. So again, Oswaldo did a great job. So instead of really thinking about belief, you really think about this free energy to optimize. And you basically, all you're doing is making approximations to allow your beliefs and the vectors to be coming from this Gaussian family, or any variational trick does not have to be Gaussian, but for Bayesian neural nets, they tend to be the most useful ones, which we did. Now, again, you can do the same. Oh, sorry, this should have not been. Now you can do the same thing here. Now they're seeing observations, and the system models are much more complicated. In particular, they're observing real images, but they're seeing very different kind of real images. Let's say some nodes are seeing things like, for here, in order to run it on a federated benchmark, we're running it. Some of them are seeing pants, some of them are seeing shirts. Can they actually learn a model that classify all of them together? And again, remember the connection to the wireless is that this is now very useful, because now the drones are seeing the visual scenery, and they have to decide what is the appropriate dynamic that they are going to share with. Okay, perfect. So I'll just stop. So it turns out that you get similar good behavior. Let me just... So I'm out of time. Okay, so then let me just stop here. Let me just go to conclusion. As I expected, I didn't get a chance to talk about empirical optimization. Basically, data-driven optimization for wireless networks. There's lots of room to use it. I just showed how it can be used for sort of distributed control of the infrastructure in combining federated learning and optimal control. I'm gonna just stop here.
Any questions on Zoom?
Did you hear one though? The linear one is too simplistic, but the actual, the complicated one, yes, I would argue almost all software parameters that you control on devices, it will cause interference, so you need to think about a joint cost, but you can control each of them in isolation. So you can potentially have a good model of, each system, and you can control it fairly well, but you really need to, they're sort of conjoined only through their cost. So in that sense, I think the model is very, very relevant. Have been able to do it. This is actually my plug. Actually, we have to do this because I noticed Naveed and Royard, the industry folks. The real challenge is data sets. So this is, so one good news is we have talked to folks at UCSD. We got tired of waiting for industry people to share data sets. So we're now looking at some of the internal data sets to the UCSD. Like all universities, UCSD runs 3 parallel Wi-Fi networks, and they have good data collected there that we are hoping to actually use some of these ideas to test on those, because data sets are really the difficulty here. It's not hard to imagine you can set these. In fact, we have done it for one building. We set up our own Wi-Fi card, but it's too small. You can't really test the ideas in terms of scalability. So we are now looking at that. And that by itself, I would say, a good research topic, curating data sets that are wireless that we can put up. So that's another. Yes, so the first thing is we are hoping to curate it to be anonymized enough and privacy preserving enough that we can share it with the whole community. Then we will apply our own, my own students will apply our algorithm, but hopefully the whole community can apply some of their ideas on these things. We saw like almost everybody was talking about it, but like Heiji was talking about cluster federated learning, Alejandro was talking about like autonomous wireless and so on. Every time you look at the data sets for all of these, they're either simulated, which at the end is not reliable and more than the simulation that you've set up, or they are not open for you to test your data. And a lot of times, at least in alignment, another application when this is very useful is alignment, like millimeter wave alignment, because you could do this. But again, a lot of times the stuff that somebody has in their paper, when we try them, our data sets is just completely falls apart. It's very sensitive. So the first goal, and that's where I would like to hear as much people who are interested, is curating a data set that we all believe is representative enough. But yeah. Some part of it, yes, but some part of it not. Like, so for something, the learning part, I think we can do it passively. And that's the first goal. And what we have shown in our theoretical results is that if you get the learning right and it converges fast enough, then the controller will take care of the rest. So at least in some good scenarios, the learning is really the bottleneck, not the control. Yeah. Thank you.
All right, I will introduce our next speaker, who is Salmon Vestmeyer. Okay, so I'll introduce your bio and then that's what so Salmon Vestheimer received the Bachelor's of Science degree in Electrical Engineering from the Sheriff University of Technology in 2003, and the Master's and PhD degrees in Electrical Engineering and Computer Science from the University of California at Berkeley in 2005 and 2008, respectively. He is the Dean Professor, the inaugural director of the USC Amazon Center on Secure and Trusted Machine Learning, Trusted AI, and the director of the Information Theory and Machine Learning, VITAL, Research Laboratory, Electrical and Computer Science Department, University of Southern California. He is also an Amazon Scholar with Alexa AI. His research interests include information theory, large-scale distributed computing and machine learning, secure and private computing and learning, and federated learning. He's received a number of awards for his research, including the James L. Massey Research and Teaching Award from IEEE Information Theory Society, the Information Theory Society and Communication Society Joint Paper Award, the Presidential Early Career Award for Scientists and Engineering, PECASE from the White House, President Obama, the Young Investigator Program, YIP Award from the U.S. Air Force Office of Scientific Research, the National Science Foundation Career Award, the David G. Sechristen Memorial Prize, and several Best Paper Awards at conferences. He has been the general co-chair of the 2020 International Symposium on Information Theory and an associate editor of IEEE Transactions on Information Theory. So without further ado, I would like to welcome on stage Dr. Avestamar.
That was a very difficult task, but you did great. So what should I do?
If you could connect to Zoom and then I can focus your screen. Yes. And where would I put this? Yes, if I could hold it, look at it.
No, that's great. Okay. All right. Hi, everybody. So I think my talk is going to be about the elephant in the room, which is LLMs, right? And how to make federated learning relevant in the new world of generative AI and LLMs. The work is in collaboration with several folks I have listed here. All right. So again, no surprise, everybody knows, everybody is talking about generative AI, LLMs, they comes to do from A to Z. And the question is, given these models, why would you want to do federated learning to learn from private data? Is there any reason to do it? All right, so if you look at it, there are like two sides of the board. Left side is driven by generative AI, large language models. These are gigantic models pre-trained on as much public data that you can collect. Right? And they are powerful, multimodal, they promise a lot of things. On the right side is like a federated learning, maybe focusing on a smaller models, but the advantage is really accurate data or private data or domain-specific data. Okay, so it's kind of, it has much data, much higher data quality than what is fed to generative AI models. So in general, I believe both of them are going to be valuable, meaning that you need pre-trained models because they can solve many problems. They are very capable. You also need federated learning models because they can fine-tune to domain-specific data. And the question I wanted to focus on, two questions for this talk, maybe the first one I get the time to do, is going from left to right. How would you use generative pre-trained models, right, like ChatGPT, like other GPT-4 in federated learning? So we shouldn't start just doing federated learning separately. Maybe we should benefit from these large models. So how can we leverage them? The other one is going from right to left. meaning that if the trend is going towards larger and larger models, then we should think about how to make federated learning amenable to large model training. Right? So how to do training of larger models across mobile phones, IoT devices, etc. So let's start with the first question. How would I use GPT in federated learning? This is the recent work that we have been doing, and I can mention to you the results we have. To do that, let me tell you the thought process on how we approach the problem from a real-world scenario. So let's say you have an experimental setting, you have 100 clients. Together, they want to train a computer vision model for image classification. And there are like 3 problems they want to solve. A simple 10-class CFAR10, a more complex CFAR100, and a very domain-specific 102 flower. So 102 flower dataset is like a lot of flower images with a specific characteristics. Okay, so it's really domain-specific, not just a simple daisy flower, going to the detail of different kind of categories of the flowers. Okay, so in all of these cases, you have 100 clients. The data is going to be distributed, the training data across the clients. It's like a true federated learning scenario. Maybe users have been taking images, and they want to collaborate for training. CFAR10, CFAR100 is like low resolution images. Flower 102 is like a high res images. Now let's start by just these users trying to do federated learning. Okay, and come up with a good model for classification. What can they do? Here are the results. For example, we looked at training VGG19. There are some algorithms in federated learning, like federated averaging, the basic one, FedProx, scaffold, right? And this is like the results you are going to get. CFAR10, by just pure federated learning, maybe the best algorithm can give you 75%. CFAR100, much more challenging, maybe you can get to 31%, and Flower 102, you get to 33%. Okay, so that's kind of like a starting point using FL. Now, what can you do next? There are some works in the FL community on using public data together with it. And the idea is that maybe while the users have new data that they bring in, right, then there is some public data available on the server that can be leveraged for data. These are some of the works: Moon, FedDF, ESFN, FedET. These are the works in the past couple of years. What they do is like they look at a combination of using the public data, maybe to come up with a contrastive loss to help the users to train, or maybe doing a distillation for better aggregation. Generally speaking, of course, more data you have, it's going to help you. So they boost the accuracy a bit. For example, maybe from 75 you can get to 78 using FedET. Here you get 35. What we are seeing is, as you go to very domain-specific problems like flower, it is very difficult to collect public data to help you. Right? The public data that you get on flowers, they're not very specific. It's not going to tell you like really what are the detail and categories of the flowers. Okay, so that's where we're just using public data on the server. Maybe for basic problems, you can get advantages, but for very domain-specific problems, they won't be able to help you. So what can you do? Another thing that is gaining traction in the FL community is using instead synthetic data at the server. So how can you do that? There are 2 methods. One of them, FedGen, ICML, and DynaFed in CBPR this year. What would they do? For example, in FedGen, the goal is for the users to collaborate together to train a small generative model, and then use that generative model to generate synthetic data that can then be used for federated learning. Okay, so it's kind of the users collaborate, train a generative model, which is matching their own distribution, and then keep generating data with that, passing it to the clients for better federated. That's one approach. The other approach is, instead of training a generative model, try to invert the trained model to come up with a model inversion and synthetic data creation. It's kind of, the trajectory of the models. At the server, you try to figure out what is the model, what is the data that could result in such models. So inverting it and get some synthetic data and use that in the training. Nevertheless, these are two methods that have been looked at. You look at them. The first thing you realize is it's very difficult to apply these methods for training large generative models because you don't have much data. So that's where maybe you can train a very small 3-layer CNN like ConvNet. And when you do that, you get a little bit improvement, not much. So maybe for small problems, like what those papers have shown, for smaller problems, simpler ones, you can get benefits. As you go to challenging problems, C400, don't see much benefit. Also, they won't converge if you go to very specific data types. And the reason is really with these small, generative models, the quality of synthetic data that you are going to get is so low that messes up your federated learning. And that's what we have been seeing. All right, so what can you do to go beyond that? It's kind of, we looked at just using FL, using some public data alongside of FL, using some synthetic data. And that brings us to our method. We call it GPT-FL, which is GPT-assisted federated learning. So how could you do? So here is one approach. It's kind of the first part is, let's say we are solving an image classification problem. We need to generate synthetic data, for example, across a variety of tasks we want to solve, maybe airplane, bird, dog, C400, or maybe different type of flowers. Then you need to use a generative pre-trained model to create synthetic data across those labels. The first thing you need to do is to do some prompt engineering. Means that you have to create some prompts that are matching those labels. For example, for airplane, maybe a prompt can be large commercial airplane in the blue sky. And as we all know, the prompt matters a lot on the quality of synthetic data that the models can generate. After you have those prompts, then you are going to feed them to your synthetic image generator to get synthetic data. Once you generate a lot of synthetic data, then you can use that to pre-train your model, then pass it to the FL world for the users to further improve it. So that's going to be the pipeline of GPT. To make it more specific, we assume that these pre-trained models, you don't have access to it. The only thing you have access is like a black box, an API. For example, for prompt creation, we use ChatGPT. Okay, so that's an LLM. You say, create a prompt for airplane, for bird. It's going to generate a variation of the prompts. Then put that to a stable diffusion for synthetic data creation that you can see on the right. Now you have a lot of synthetic data, train our VGG19, and then pass that to the federated learning clients to further fine-tune it on their own data. So very modular scheme, you can apply it to any other federated learning problem as long as you have pre-trained models in those domains with a mixture of fine-tuning and synthetic data creation. So what can you get? What we are seeing is that across all the three settings, you get improvement and substantial. For example, right now on C410, you are getting to 82%, C400 from 30s, you are getting to 47%, and Flower 102, big boost. One reason for here is that you don't have much data at the clients to come up with a good feature extractor. With the synthetic data, they become very powerful on feature extraction. Then they can focus on more how to use the real world data to use those features for better classifying. That's why you are getting these substantial gains. So it's very promising, right? And this is one side of the benefits you see, meaning that you can improve the performance. There are other benefits. For example, here we are looking at the communication requirement, like how many parameters do you need in federated learning, how many runs you would need. What you are seeing is that these using a good pre-trained model at the beginning, the model converges much more rapidly. So you have much less communication burden on your network. You have much less number of runs that you need for federated learning. And these things matter a lot as we are moving into resource constrained edge nodes. Right? So it's not all about accuracy, it's also making a system much more efficient and much faster. That's other advantages you can see. Maybe one way to explain it is, for example, with the other method that I mentioned to you, they generate synthetic data, for example, DynaFed. this is the quality of synthetic data they can generate. It's very low. But then, as you can imagine, with the GPT-based methods, you are really using high quality synthetic data that is helping you to improve the performance. All right, so maybe a couple of other questions. For example, maybe you would wonder, did you need FL at all? Could you just create synthetic data and solve the problem? As you can expect, the answer is no. For example, here on the first column, we look at the scenario that we generate 3 times the federated learning data using the GPT model, the stable diffusion. Like even if you have 3 times more data, still your accuracy is lower than, or sometimes substantially lower. For example, in Flower, you cannot pass 30% by these pre-trained models, right? Huge gap to the GPT-FL based. So the answer is no, by just generative pre-trained models and using them to, train your model, you cannot make progress on domain-specific problems. So you still need private data to go from 30% to 7%. Yeah. Right. No, that's a good question. So yes, the generative model is broad, but the same as for C410 and C400, right? So that's why there, for example, C400, you only get 41%. Here you are getting 62. So still, even you see, there is C400 is also generic labels. There is nothing special. Flower is gonna be the domain specific that you see huge. Okay, so the short answer is, as the problem is simpler, maybe these generative pre-trained models are good. As they become more challenging by themselves, they're terrible.
But I was guessing was it like 400 or something, you still have so many classes that I don't remember the data that you picked, but each agent maybe gets paid the same.
No, but here is centralized training. The results here has nothing to do with the agent. It's like I just keep generating the data. For example, let's say your goal is to come up with a classifier that can identify drones. Let's say you're working on military. You want to have a classifier for drones, for, I don't know, rockets, etc. Then one way is you use these pre-trained models to generate many samples. Then they train your classifier on that. Don't use FL. Another scenario is that you do FL across maybe actual, cameras that have collected the data, and then you can see the benefits. Maybe another thing you may wonder is, is the gain coming from the pre-trained models seeing your test data? Right, so you remember here, you are using the pre-trained model to generate some synthetic data and then train the model on that, right? So that can happen, especially for a stable diffusion. They're trained on a very large data set of images and many other images. So this problem is difficult to answer for images because there is a lot of images and we don't know what is fed into it. And probably anything they could collect, like within C400, they have already fed into it. Okay, so the way we answer that, we look at it for another problem, out of domain, data generation. So we look at speech data, audio data. In that case, you can use a speech T5 model, which is pre-trained on a data set, library speech audio data set. And the problem is like a Google or background ambient noise, ESC 50 problem. So since these two are out of domain from the original trained model, they have nothing to do with each other. It means that the original pre-trained model has not been exposed to the domain that you try to solve. On images, stable diffusion has been exposed to all type of images. Here, we don't have that problem. Still, you can see if you only use the pre-trained model, your accuracy, for example, for Google Command is 26%. Then you use the GPT-FL, right? You are getting to very large accuracy, 83%. And so it's kind of together with FL and the pre-trained model, now you are getting a whopping performance, not only over synthetic data, but also federated learning methods. All right, so that's maybe my conclusion for the first part. I think what we are seeing is generative pre-trained models by themselves and federated learning model by itself may not be sufficient. All of them are good, but you have to combine them together to really see the benefit of the both worlds. GPTFL that I proposed is like a starting point to leverage the pre-trained model as a black box to augment and help with federated learning scenario. But I think there is much more that can happen. All right, so maybe I can pause here if you have questions on the first part.
Do you do anything by the FL model if they were to take all of that data, forget about privacy, and make
Yes, so these are the results on FL only.
No, I understand. GPT
Yeah.
right? And then whatever you're right now giving them.
Oh, then you send them those? Of course not.
No, I'm saying most probably you're just almost going to be as good.
Yeah. No, then this synthetic data, where does it reside?
The synthetic data is you're learning some models, right? On the synthetic data. I'm just saying after the synthetic data,
Yeah.
All the data that the fed agents are seeing.
Is like to do centralized training.
Centralized. I suspect you're going to be almost no loss associated.
Exactly. Yeah. But here is kind of the setting. Maybe okay. So I mentioned to you one of our collaborators, Amazon in this case. So the real world scenario is going to be the following. Alexa. The debate is: should they just work on LLMs as conversational AI, or go through all the hassle of learning from private people's communication, etc., to have a more personal communication? Okay, so that's kind of a real debate. The answer is no. If you just use the generic chatbots, right? They cannot understand your specific demand. When you say play this song, or should know a little bit about you, what has been your history, what are the other things you have been asking for, etc. Right? But for them, they can start with a pre-trained model that they have access to. Use that to generate samples for the type of problems they want to solve, and then use the FL data that they cannot bring to the cloud because of the privacy to further improve.
And the question that I guess I'm asking, because I would also say this is just a personalistic added. What will be the benefit of federating?
Oh, federating is like a flower. It's like, think about, you want to solve the problem for many flowers. Each person may have only a few samples of flowers. Or in the other case, you have a conversational model, right? You are not exposing the model to all type of musics. Right? Maybe, he's interested in classic, yeah, but then somebody else in your home. I think if you make it specific to Alexa, it's going to be their goal is. Yeah. Yeah, so there is a personalized version of that. But this is more of the general idea here is you have access to a stable diffusion. You want to solve a flower classification problem. How would I use that together with FL? And the message is FL by itself, is good, but not good enough. Pre-trained model by itself, in that case, terrible. Combining them can be better. All right, I think I'm over the time. Maybe the second question I can just mention. The second part was like how to move federated learning towards large model training. Maybe I can mention to you just the approaches. So in general, this is an area the community has been working on it a lot in the past couple of years. There are kind of three promising approaches. Either you do a sparse training of the model. Another part is you do a sub-model training, like a low-rank decomposition of the model, or you do knowledge transfer. So in the sparse training, it's kind of you create a mask, you focus on some fraction of the weights to do the training. The advantage is they are memory and bandwidth efficient. Typically, you don't incur much loss in the accuracy. The problem with it is they are memory efficient, not compute efficient, because you cannot accelerate sparse tensor computations. So it's like as if you are doing the entire process. Then submodel training is very good both on compute and memory because your submodel is dense, so you can accelerate it. Also, your memory is going to be smaller. Typically, identifying the submodels is difficult, so they can incur some loss. On knowledge transfer, you train a smaller model, like a student model at each user, and use knowledge distillation for a teacher model training. It's very good on both memory, computation, the size, so it's great. The only problem is you have to communicate more features to the server for the knowledge distillation. That may incur maybe more communication, maybe more privacy degradation. Nevertheless, on these three, I have mentioned some of the works in our group that has addressed the problems. If you are interested, you can take a look. So I'm not going to go to details. So let me to the last slide. All right, so as a conclusion, I think we understand there is the FL side, there is the generative pre-trained model side. I think there is much that can be done to bring the two together and achieve. For example, do using generative pre-trained model assisted federated learning, or do federated learning of large models. Given that we are in MLSys and resource constrained edge nodes, maybe I can mention something here. What I have seen is if you want to do systems research on federated learning, especially cross-device federated learning, a bottleneck is having a test bed that you can test your experiments. That's why, for example, last year, Meta, they could have their Papaya work because they can test it on millions of mobile phones. We are in the research community. We don't have access to such test beds. At FedML, the company that we have our own mobile test bed for cross-device federated learning. We are making that available to select group of research groups that you have already an algorithm. You're at a stage you want to do a systems study of your algorithms. We can provide that so you can scale and do a study of your algorithms. If you're interested, this is something you want to do, like test it in real world, right? Reach to us and we can give you access to that test. So I will end it with that. Any more questions?
Presentation. I believe we have our lunch break at this time to be around an hour. So we will reconvene at 12:45 following our lunch break.
Great. So do I just connect to the Zoom or?
Yes, if you can connect to Zoom, just display it on your screen, and then I will focus you on, and you'll be like the head of the Zoom.
And I think I don't need this.
Oh, you don't need it?
Yeah, because I thought that,
Oh, directly. Okay. Yeah, you're fine. I'll return this.
What's the Wi-Fi again?
Wi-Fi password. Conference, one word, all lowercase. Yes, for MLSys. Yep. Okay, welcome back to the workshop on resource-constrained learning and wireless networks. We are starting our paper presentations following our lunch break. So I'm going to pass the speaker to the paper presentations. Best of luck.
Hello everyone, my name is Josh Home from University of North Carolina at Travel. Today I'm going to present my paper on enabling efficient and effective AIoT with decentralized hierarchical asynchronous learning, the HKFL. And this is a collaboration work with the Intel Lab. And here's the outline for today. First, let me give some background and introduction. AIoT has become increasingly important for modern AI applications, such as smart home, healthcare, transportation, and smart camera. To prevent sending a large-scale data and privacy leakage by sending data to central server, like conventional centralized machine learning, federated learning is a key enabling technology for AIoT, especially for large-scale data and data privacy preserving, because you only need to send a local model to the central server instead of sending all the data to the central server and perform the training. And mostly the classical federated learning relies on frequent centralized model aggregation, which may suitable for single hop IoT network, where the IoT devices are connected to each other and the central server over single hop cellular or Wi-Fi connection. However, it's not the case for federated learning in multi-hop network because it consists of a mesh of interconnected wireless IoT devices. And each node needs to relay the data toward the central server. As a result, classical federated learning is not suitable for multi-hop IoT network. And here's the limitation of the federated learning. Here's the limitation of the centralized learning in multi-hop networks. First is the scalability issue from the communication bottleneck and single point of failure around the central server. Second, it's not robust because each communication route depends on the cycles of slow worker. As a result, scalability and robustness issues lead to slow convergence time. Another solution is that we can adopt decentralized learning because it can reduce the learning traffic around the central server and balance out the traffic flow among network topology by just exchange the model within single hop among neighbors. But again, it still has the scalability issue when the number of workers increases. And most of the decentralized learning focus on synchronized optimization, which is not robust in heterogeneous environment with the presence of the stragglers. As a result, the decentralized learning also slow down the convergence by scalability issue and the impact of the stragglers. Therefore, in this work, we propose a decentralized hierarchical asynchronous DHAFL approach to improve scalability, robustness, and resilience by simply combining hierarchical learning and decentralized asynchronous model aggregation together. Basically, we use hierarchical learning to enhance the system scalability with two-stage model aggregation to reduce the federated learning traffic. And we use the decentralized learning to reduce the communication congestion and the single point of failure around the central server by exchanging model within one hop neighbors. And with the asynchronous operation, it can reduce the impact of straggler because it does not need to wait for slower worker from the neighbors. And more importantly, we have implemented an experiment, the HAFL, in the real wireless multi-hop testbed to show that it's robust to the heterogeneous IoT environment and it can accelerate the convergence speed of the model training in the real testbed. And in particular, the HAFL relies on a two-stage module aggregation algorithm. In the lower abstraction level on the left-hand side, at the edge level, in the stage 1, each edge server updates its local model by aggregating model from its assigned worker using a set average. And then on the right-hand side, at stage 2, it communicates with one hop neighbor edge server to update the shared global model and to mitigate the effect of staggering. Each edge server uses an asynchronous model averaging approach to update its model based on received model from neighbors without waiting for slow workers. And with the advantage of the hierarchical model aggregation at edge level from first stage, it can reduce the self-learning traffic, which leads to high scalability. And also, with the advantage of decentralized model aggregation at the global level from the second stage, with the asynchronous operation, it can avoid the staggers and lead to high robustness. And here's the experiment setup of our testbed, the wireless multi-hop edge computing testbed. For the hardware setup, our testbed includes 10 wireless edge servers, each with a wireless router for communication and intermediate cellular node for computation. And each edge device, we deploy each edge device with 3 virtual workers. So total, we have around 27 virtual workers for local training. And for the field learning setup, for model and dataset, we test with MobileNet with Cipher 10 and 5 layers of CNN model with FE dataset, and all experiment has been done with non-IID data. And we train at least 30 epochs for each virtual worker, and each epoch with 5 local rounds. And we add 40-second delay to each local round for the speculative worker. And in this experiment, we compare the HAFL solution with centralized field learning, hierarchical centralized field learning, and decentralized hierarchical synchronous field learning as the baseline. As you can see, in the top 3 figures represent the average local training time of each edge server, and the bottom figures represent the test accuracy versus walk-hop time. On the left-hand side, in no straggler case, as shown in figure 8, all of hierarchical field learning-based solution outperform the flat centralized field learning baseline around 2 times faster in terms of the walk-hop time convergence, because hierarchical field learning can help reduce the field learning traffic and improve the scalability by aggregating local model at the edge server before sending to neighbors. And on the right-hand side, when a single straggler is introduced, as shown in figure B and C, you can see that in the figure E and F, all solution experience in increase of training time, except the HAFL that less affected by a straggler, because it can allow fast workers continue their own training without waiting for a straggler, which is 4 times faster than the baseline centralized field learning. And another experiment is that in this table, they present a convergence walk time of each fair learning method, such as the average CFL over various number of stragglers and locations. And the percentage of these stragglers represent the number of each server that are affected by slow workers. We can see that the HAFL can improve convergence speed up to 8 times over the classic fit average CFL baseline when dealing with 10% the speed of the stragglers. And as the number of stragglers increase, the HAFL can still achieve faster convergence speed compared to others. And in conclusion of this work, we propose the HAFL model aggregation method that combine decentralized asynchronous learning and hierarchical learning together, because decentralized learning with asynchronous approach can avoid speculation and lead to high robustness. And hierarchical learning can help to reduce the learning traffic, which lead to high stability. As a result, the HAFL can avoid speculation and reduce the learning traffic, so we can achieve high robustness and high scalability learning solution. And our experiment results on physical testing show that the HAFL can accelerate the convergence speed of the learning training up to 8 times compared to centralized learning baseline. Thank you and patience.
I think I have any questions. Very well presented.
Thank you.
Good.
Yeah. Sure. Yeah.
So hi everyone. I think it's muted. Okay. Oh, okay. That's fine. So hi everyone. I'm Jackie Yuan from New York University. I'm going to present a paper titled "Scalable Feature Compression for Edge-Assisted Object Detection over Time Varying Networks." So first of all, a little background on our work. In many applications of visual analytics, we have a computationally constrained mobile device that captures very high resolution image data, and we want these image data to be processed by a computer vision network that is really computationally intensive. So one solution to this problem would be to do split computing, where we split the task network into a client model and a server model, which we call the task encoder and the task decoder. And when we do this, we need to compress the intermediate feature and then transmit it through a variable bandwidth network link. So the feature compression method would be very important to reduce the rate needed to transmit the feature, and also to keep the accuracy of the model to be high. So here are some prior works on feature compression which are not scalable. So in 2020, they used array task law to train the feature compression model end-to-end. And Yuan et al. 2022, they use a feature dimension reduction layer to first reduce the dimension of the features, and then use a hyperparameter network to arithmetically encode the features. And then DataML 2022 achieve variable rate compression by switching the feature dimensionality reduction layer. So in the bottom right, you can see a graph showing one result from UNL. So you can see that the horizontal axis is the bit rate of transmitting that feature, and then the vertical axis is the accuracy of the object detection. So in this model, they are able to achieve good performance while using very little bit rate. But the drawback is that for each point on that curve, we need a separate, we need to create a separate model to achieve those bit rates. So here is an example of non-scalable feature compression model. In this example, we split the YOLO, which is a popular object detection network. We split the network into two parts. One part on the mobile side, and then the other part on the edge server. And we compress the feature in the intermediate layer. So in this work, a feature dimension reduction layer is used to first reduce the channel and spatial dimension of the features, and then hyperparameter network is used to arithmetically encode the reduced feature. And this is a case of non-scalable model. To achieve different bit rate, different versions of this model have to be trained. So if you want to, in a variable rate setting, you would need a lot of these. You would need to store a lot of these models to achieve different bit rate. So for this work, we're proposing to use scalable compression, which is the concept that has been in the image compression framework. So in scalable compression, we compress the feature into a layered history. We have the base layer Z1 and then Z2 to Zn enhancement layer features. And with the base layer, you're able to get a certain performance. And as you receive more layers of history, your performance of the model increase. And the advantage of this is that you can adapt to a dynamic network condition, and the task encoder is fixed regardless of the bit rate, so you don't have to switch between different non-scalable models. And this is a figure of our proposed model. We achieved scalability by training different dimension reduction modules for each feature layer. So these are the different reduction layers. They take the intermediate feature and then reduce them into smaller feature tensors, which are then separately entropy coded. And at the server side, when these features are received, they are decoded and then expanded by an expansion layer and then added back before feeding into the server network. So at low bit rate, you only transmit the low layer features, and as more bandwidth becomes available, you will transmit more of these features. So here is how we do model training. We train the model by minimizing the rate task loss, which is a combination of the rate needed to encode the features, and the task loss is the loss for training the object detection. And so for a scalable model, the loss up to the ELF layer will be the sum of the rates of all the losses of all the rates up to the outlier, and also the task loss of using the up to outlier. And to train this, we use the strategy of like for each batch of training samples, we process the input from with L from 1 to M, with M being the highest number of layers, and then we update the model with the average loss over the M rounds. So here is a result when we use this strategy to train all these models. So in this model, we have 4 layers. So that's the 4 points on the orange curve. So in this case, the scalable model even outperformed the non-scalable model in the high rate range, but at the low rate range, the scalable model underperformed the non-scalable one. So to solve this problem, we think that it is difficult for the same encoder and decoder to operate the entire bit rate range. And since the computation resource is less limited at the server side, we can operate a larger network at the server side. So we train a separate task decoder for the bitrate range at the server side. So modifying the previous approach, we split the base layer into 8 groups of 1 channels each, and we train this model by feeding these 8 layers into the into a new server task decoder network. And we train during this training stage, we freeze the task encoder network and also the task decoder network for the high rate, so that the performance at the high bit rate is not affected. And here is the result of using this 2D decoder model. Is the green curve over here, and you see that for this green curve is able to match the performance of the non-scalable model throughout the entire bitrate range. And in here I show that for this bitrate range, it uses the low rate decoder, and then at this high rate range, it uses the high rate decoder. And even though the decoder at the server side is different, at the encoder side, which is the mobile side, only one encoder needs to be used, which would be good for the resource constrained mobile device. So in conclusion, our work proposed a split computing model with scalable feature compression. Scalable feature compression allows us to adapt the model to a dynamically varying network, and the performance of our model is comparable to the non-scalable model when we use multiple decoders. And for future works, we would like to look into better strategy of training the scalable model to reduce the training time, because the training strategy right now it needs to run through all the layers for each batch, so that is probably not very efficient. And also, we would like to look into more sophisticated methods to generate the layer history. So right now it's only a linear transformation. If we are able to use more sophisticated methods, we can probably reduce the redundancy between different layers. So that's this. Yeah.
Here's on the last slide. So other possible future. Which methods have you worked at? Or have you kind of like evaluated the main methods for each?
Yeah, not yet. So right now we only use to generate each uh, each layer. We use a single convolution layer, which is pretty much just a linear transformation. But there are also, we have looked into some works in the scalable image compression domain where they can use feature reuse between different layers to enhance the features after it's being decoded. So I think we can look into some ideas like that to adapt that for this feature compression.
Yeah.
I think so in this case where we focus on like split computing to reduce the computation on the mobile device, and this is more like we're mostly focused on like training the model and then do the inference. But I think like maybe for federated learning, I think we also need to transmit data between like the mobile and probably a centralized server. So I think, and if we compress those data, the performance might decrease. So I think in that sense, we can it might be also related to the federated learning.
Great. Have a 15-minute break scheduled between the papers. So we are going to return at 1:30. So 15 minutes from now.
Hi, Irvin. This is Ravi.
Hi, Ravi. This is Olga.
Hi, Olga. Good afternoon, good evening. Thanks
Hello.
for
Good
joining. Yeah, just checking with, just looking at this again. So, Irvin, I'm one of the organizers. So I believe you are hosting the workshop today. Is that right?
Yes, yes, I am.
Okay, thank you. Are you planning an introduction to for Olga?
Yes, I have like a paragraph I was going to read for her.
Okay, perfect, perfect. Just making sure. Okay.
Okay, great.
Ravi,
Uh-huh.
is that okay if Sergey joins? You wanted
Of
to.
course, yeah. I think, yeah, feel free to forward the Zoom invite.
Oh, thank you.
Yeah. I don't know.
Yeah, sorry about that. You can start whenever. Thanks.
Hey, Erwin, did you want to make an introduction or?
Oh, sorry. I guess I was introducing, but the network went down. I
Yeah,
guess I
you were
will
not on
introduce-
you were not online. Sorry.
Oh, okay.
Okay. Thanks.
All right. So I would like. Oh,
Oh,
yeah,
sorry.
I'll introduce again. I'd like to introduce Olga Golanini from Tampere University. Olga Golanini received the Bachelor's of Science and Master's of Science degrees from the Department of Applied Mathematics, Peter the Great St. Petersburg Polytechnic University, Russia, and the PhD degree from the Tampere University of Technology, TUT, in 2015. She is currently a senior research fellow at Tampere University. Her research interests include applied mathematical modeling, and analysis of wireless networks, and statistical machine learning. So without further ado, Olga, you have the stage.
Thank you very much for the introduction, and good afternoon, ladies and gentlemen. And today I stand before you, or rather sit before you in the comfort, in Finland, in the comfort of white nights and what we call here green winter of 10 Celsius degree. I was really looking forward to join you in Florida, but apparently life had other plans for me. But anyway, even so, I'm thrilled to be here to meet you, at least virtually, and have this opportunity to discuss this new direction we have recently started in our group at Tampere University. As I understand, most of you are passionate about machine learning, distributed learning, and communication networks. So I thought it would be a great idea to discuss how machine learning algorithms could be improved with the methods of social sciences. And today we wanted to, I wanted to talk about so-called collective human intelligence. This is a quite old field of at the intersection of cognitive sciences and social sciences. And it pays a lot of attention to how the human consensus can be reached, which could be very useful for the machine intelligence too. But the target of this talk is not to go deeper into technical details, but more like to navigate the surface, scratch the surface, and explore the footholds, the initial footholds, and fundamental concepts of collective intelligence. And with that, I will switch off my camera because I'm also a bit worried about my bandwidth, and we'll continue with the slides. First of all, thank you for the introduction, Erwin. I actually wanted to, just a brief reminder, my education is sort of a product of the intersection of applied mathematics and wireless networks. And I got my PhD at Tampere University of Technology, where my passion for networking was ignited. But before that, I got my skills in applied mathematics from St. Petersburg Polytechnic University. And then I have had the privilege to join the esteemed Tampere University for advanced study when I'm a senior research fellow. And Tampere Institute for Advanced Study is a big and diverse group of different scholars, different researchers from completely different areas. We have people from social sciences, from history, from physics and communication sciences and whatnot. And that gave me a unique perspective, multidimensional perspective on how we could drive multidisciplinary research and how we could search for inspiration in different areas that we got education in. And here's, by the way, the winter picture of Tampere, because we have approximately 9 months of winter. So I thought that would be the best image of the place I live. And here is a brief outline of the plan for today. We are going to talk a bit about collective intelligence concept as a part of social sciences, and then the main laws for non-networked part of collective intelligence, and then we'll talk about collaborative problem solving, the key part, which I hope would be inspirational for many. And then if we have time, we'll look at the numerical example, because there are already, even though this is a relatively new idea, there are already papers who explore the simplest concepts of collective intelligence applied to machine learning and successfully did that. Then we'll conclude the talk with the open questions and general conclusions. And the history of our group was as follows. We started with the analysis of heterogeneous networks, heterogeneous wireless communication networks. And then we also looked at collaborative learning in heterogeneous networks, which included heterogeneous everything, heterogeneous channel, heterogeneous hardware, computational capacities, and heterogeneous data for collaborative training. And we spent quite a lot of time trying to mitigate the effects of heterogeneity, the detrimental effects we thought at the time, but the diversity, the heterogeneity is not only a drawback. We started looking at diversity as an advantage, not the challenge. And the diversity of opinions, diversity of entities has been explored in the field of human collective intelligence. And from our perspective, from the perspective we are interested in, there are two main branches, which is called wisdom of crowds, and we'll discuss it a bit later. And the second is collective problem solving is the key target of today's meeting. And I wanted to mention this famous experiment. Probably most of you are familiar with that. A famous statistician, Francis Galton, in 1906, like more than 100 years ago, carried an experiment when he called around 800 villagers to measure, to estimate the weight of an ox. And the collective, of course, the estimates were wrong and were not exact. Some of them were closer to the actual weight, some of them were further away. But what was exciting and surprising for the statistician is that the average value was just 0.5 kilo, 1 pound away from the real weight of the ox. And that inspired 100 years ago a huge area of what is now called wisdom of the crowds. And if you Google it in Google Scholar, you could find around 18,000 mentioning in the research society. So this is a really big area. And yeah, for the interested reader, I would refer to the actual paper, which is more than 100 years old. And well, this is a very famous experiment. There are different variations of that, like maybe estimating the number of candies in the jar or something like that. And this is one of the most known examples of what collective intelligence is. And we define collective intelligence as a field which studies how groups of individuals act together more intelligently than a single individual in different task solving. There are many definitions more broadly that's based on the definition of intelligence, like the philosophical definition of intelligence. But the key point is that people, like humans, can improve their decision-making strategies and their accuracy by discussing and brainstorming, just as happens in real life when we discussing ideas and provide arguments and try to evolve based on those arguments. And that works not only for humans, but for animals, for other organisms, and even for cells. And some biologists say that everything is collective intelligence in our world. And the difference between these two subfields, how we define that, is in the presence of the networking, the communication networks. The wisdom of the crowd search answers that are just derived using the aggregation rules, like in that experiment with the ox. And the collective problem solving is a dynamic process which includes communication between entities, as in that example of brainstorming, when several individuals provide arguments and not just the final estimates, but some reasoning process is behind the decision making. And as a computer science / networking engineer, I would be more interested in this collective dynamic problem solving. And first, I wanted to cover the basics of non-network approaches, which is related to the wisdom of the crowd. And there are two main, the most famous laws there. The first one is crowds beats averages, which means that the average individual error is not less than the collective group error, but in most cases it should be greater than the collective group error. And there is this famous diversity prediction theorem. You could find like in numerous videos in YouTube, for example, when everybody cites this theorem. And here's the formula, but basically this formula means that the group error is the difference between the average individual error and the group diversity. And the whole idea of collective intelligence is to increase the group diversity, to decrease the group error. Personally, everybody talks about this theorem. It's just like foundation of all the principles of collective intelligence. But there are as a person who comes from applied mathematics, I have some concerns about this formula, and some things here are not that simple. I think there should be some strong assumptions on independence of some parts of this equation. But the general principle, the philosophical principle here is that we need to increase the group diversity to decrease the group error. But it's not, I think it's not that simple as they say, but the general principle is like that. And collective intelligence provides a number of different tools how to measure the accuracy of the group and the benefits of the group and the group decisions. Some examples, just the basic examples, is collective intelligence score, which just compares the performance of the average performance of the group and average performance of individual members, or something related to variance, which is the parallel intelligence factor or collective intelligence factor. And it measures intergroup differences like diversity we want to look at. And just another example is Shannon-Wiener index, which looks very similar to the entropy formula. And this example is just to remind that this area is not that far away from information theory, for example. It uses the same principles, and we could easily understand papers from social sciences. And collective intelligence inspired quite many machine learning methods, optimization methods in computer science. And a couple of examples here. The wisdom of crowds as a static decision-making inspired such algorithms as ensemble algorithms like bagging, boosting, stacking. This is remotely based on that experiment with the ox. And collective intelligence, most importantly, emerges from the interaction. And that's what many biologists observe. And this inspired so many swarm optimization algorithms like particle swarm optimization or ant colony optimization and so on. But the main idea here is to take a step further and consider not just simple entities like particles or ants or bees, but something more intelligent, even with the level of arguments and sort of intelligence as the large language models can provide. And can we create a system which would use those complex models to build a decision-making system by mimicking human-like interactions between the entities? And the social sciences would help, well, I believe that this area would help to mimic human experts in brainstorming, in collective reasoning, and to create more efficient aggregation scheme than just ensemble algorithms that are fairly old, but quite beneficial for a certain series of problems. And we select collective problem solving because of its dynamics and because of its dependency on the communication networks between the entities. And collective problem solving, the distinctive features of collective problem solving is that we are trying to solve specific problem iteratively by sharing the information and taking the information as the input and adjusting our estimates of the machine model in this case. And we believe that collective problem solving offers core principles and communication network architectures to improve the collaboration of advanced machine learning models. And this is probably the key slide of this talk, the key findings for collective problem solving, the quite recent conclusions from the social sciences perspective, is that the key network property, the first one is that the key network property, and network meaning the connection between machine learning models or humans, so either social connection or some kind of information channels. The information efficiency is the key here. The information efficiency is defined, vaguely defined by the average simple path length in a communication graph. And here is an example of an efficient communication network and inefficient communication network when we don't have as many neighbors as we could have in a complete graph, for example. An interesting conclusion is that the effect of network structure is always driven by the task complexity, and the collective intelligence on complex tasks is improved by, this is a counterintuitive conclusion, but we need to reduce information efficiency to improve the benefits of collective intelligence in complex tasks. In simpler tasks, it works the opposite way. The better the connectivity of the graph, the better would be the benefits from the collective intelligence in this case. As I mentioned before, there are not so many results on the use of social sciences and collective intelligence, but I found a couple of papers, recent papers this year and 2 years ago, when researchers explored the Groot consensus, and the Groot consensus is a mathematical model for reaching human consensus, but it dates back to the year 74, so the approach is really old. But the researchers here managed to demonstrate that the collaborative solution, the use of collective intelligence is beneficial, is more beneficial than just a simple averaging of their opinions or the performance of individual agents. And in these two papers, they demonstrated using different methods, more complex, like deep learning models, and simpler models like lasso and ridge regression. They demonstrated that there is a benefit of from using this collaborative approach compared to Fed average, Fed prox, and local training. And they proved that method is particularly effective in the presence of heterogeneity, that diversity which we started from among the individual agents and training data or model architecture. And I believe this is a very important proof of concept, even with the presence of this simpler and fairly old approach, the group consensus, I mean, we managed to get some interesting results here. And of course, at the intersection of computer science and social sciences, there is a multitude of open research questions. Of course, we need to investigate issues of trust, reliability of contributions, potential biases introduced by the participants, and we need to explore incentive mechanisms and, very importantly, privacy and security concerns in such system, because we share a lot of extra information, even though we might not share the raw data, we share something. And another important issue here is that scaling is an important question, because in the human consensus, which was studied 100 years old, scaling is not as big problem as a human brainstorming usually concerns several people, not thousands of people for that matter. And that brings me to the conclusions of the talk. And we believe that distributed learning can tremendously benefit from social sciences, from collective intelligence, by using the value of diversity, of diverse perspectives and diverse backgrounds of the machines, but not only machines, but in the case if we could merge human and machine intelligence, both sides could be, both diversities could be beneficial for us. And by looking at collective problem-solving dynamics, how the group works, how communications, which network density, communication density would work best for the particular task, and by pooling the collective knowledge and using different transfer mechanisms and development of this transfer knowledge sharing and knowledge transfer mechanisms is a separate open question. So yeah, well, I know we didn't have that much time, and what we managed is just to scratch the surface, but I do hope that this collective intelligence field, the area of collaborative problem solving, would inspire you to search for more accurate and better solutions in distributed learning in communication networks. And I would be happy to answer any of your questions. Hope I was within my time limit. Would be happy to answer any questions if you have any.
Yes, great presentation. The audience, is there any questions for the speaker? I don't see any.
Ervin,
Yes.
I do have a question, but I'll wait for if there are other questions from the live audience.
Anyone on Zoom have questions?
Okay, I can go then. Olga, thanks again for the excellent talk. It's a very exciting area. Particularly, I'm interested in your comments about robustness of these consensus approaches, especially as you point out the other baselines like presently Fed average, etc. So how are those being supported? Like robustness, especially in the sense that if there are few malicious actors who can try to impact the overall learning.
Yeah, well, actually, that was one of the open questions: privacy and security, and how to act in case there are malicious agents in the system. That paper I mentioned was not covering the security aspects, but that is a very interesting direction to explore, because in that more complex process, it's probably harder to understand which user is malicious and which is not. But that boils down to another open research question, is the question of trust. And in that example with the Groot consensus, there was an iterative step of updating confidence in the estimates of other agents. And with the confidence, we could probably, as a machine, as a human, or as an entity participating in this collaborative process, we could estimate our trust to the agent, and collaboratively, I think if we have a reasoning process, it's not just averaging some estimates, but it's a dynamic process with arguments, or what we do when we brainstorm the idea. I think it is possible to develop more complex schemes to take into account trust and to understand as a group, to understand who's a phony in the group, in a way, exactly as people do in real life. That's why social sciences might be a good source of inspiration.
Yeah, thank you. I'd like to know more in the future. Thanks.
Thank you.
This develops.
Yes, great
So I have a
presentation.
question, maybe a clarifying question. So have you applied some of these metrics and approaches in your work? I mean, the results were presented, but I probably missed that part.
No, not yet. It's not that we have something published. It's more like this is a very new direction, which I started as a researcher
okay.
with Tampere Institute of Advanced Study. And well, this is very promising, but I cannot share any results yet. That's why I borrowed somebody's results. But I was surprised that I found something, because, well, this seemed like a breakthrough
Not
idea.
many people are applying it yet, is what you observe.
No.
Few
I think
applications.
it's really, it's wide. There are so many white spaces here, and that's a big area to explore. So
Okay,
I
thanks.
invite everybody. Yeah, thank you so much for
Yes,
your
thank you.
question, and hope that would inspire you.
Thank you again for the presentation. Great. So I believe now we have a 15-minute break following the speaker. So we will reconvene in 15 minutes and have paper presentations. Thanks. Bye.
Thank you.
Hi, Olga, can you make me host again on Zoom if it's giving you permission? Thank you.
Sorry, I was on mute. I was asking, is that okay at the right now? Did
Sorry,
I?
can you repeat that?
Are you a host right now? I was on mute, so I was trying to talk to you, but nobody could hear. Are you a host right now?
Yes, I am host.
Okay, so if I exit the call, everything would stay normal. I mean, I will not.
I believe I would still have the recording locally. I will have to check following this. Wait, I believe it didn't send you the recording. So I'll have to check.
I don't have any recordings, but I see the sign that the meeting is recorded.
Oh, yes, I have the recording. Just checked. Thanks. Okay, yeah, we're all good. Thanks again.
Okay, thank you.
All right, so welcome back. We are going to start our paper presentations for the workshop. Our first paper is the Trained NPC, a private interface by training-based multi-party computation. So this is a recording. I'm going to put this up on the screen. So I'm going to start the recording.
Hello everyone, this is Hamid Reza Ehtaram. I am a PhD student at Sharif University of Technology. The title of my presentation is Trained NPC, a private inference by training-based multi-party computation. Consider a scenario, a client has a sensitive CT scan image and want to label it with data of cloud server. He sends some queries to the servers, and the servers, after running some processing, send answer back. The client, using the answer, obtained the label. The client is concerned about the privacy of his data. The question is, how can we perform inference on sensitive data using cloud server without leaking information to them? This is a major concept, particularly for resource-constrained edge devices such as mobile units. In the paper, we focus on inference privacy problem, where a client that has a limited computational resource wishes to employ some servers to run an already trained model on his data while preserving the privacy of his data against the server. In this problem, we have a trade-off among privacy, accuracy, computational load, and communication load on the system. There are various techniques to provide privacy in machine learning with the following three major categories. 1. Randomization, perturbation, and adding noise. 2. Secure multi-party computation. And 3. Homomorphic encryption. Applying randomization, perturbation, and adding noise technique to the client data confuses the servers and reduces the level of information leakage at the cost of sacrificing the accuracy of the result. Several works partition a deep neural network between edge and cloud and offload the computation of some layers to the server. Those papers only consider the input privacy and do not guarantee the output privacy. This means some labels of the input data are exposed to the server. Also, their performance depends on heavy computation on the client side. Secure multi-party computation exploit the existence of a cluster of servers, some of them non-coding, to guarantee information theoretic privacy. The shortcoming of this solution is that it costs the network a huge communication overhead due to the need for exchanging encrypted data. Also, some specification in the setup of this approach, like polynomial approximation and finite field, make it challenging to use in deep learning. Homomorphic encryption creates a secure framework between the client and server that allow the untrusted server to process the encrypted data directly. However, the computational overhead of homomorphic encryption is very high due to the complex mathematical operation. In addition, it's based on computational hardness assumption and does not guarantee information theoretic privacy. Here we propose trained NPC as an alternative approach to preserving privacy in offloading ML algorithms in a multi-server setup. Our key idea is to design the queries of the server such that they individually don't leak information to the servers, but jointly inject the data into the system so that we can achieve a high level of accuracy and privacy at the same time. The figure shows a motivating example of trained MPC framework for inference privacy. The client uses a very strong noise where its standard deviation is 70 times of that of data. The client send data plus noise to server 1 and data minus noise to server 2. The servers apply some neural networks and send the answer back. The client, by a simple addition, obtain the label. Thanks to the very strong noise, the server cannot infer anything about data and its true label. The high performance of our method comes from the fact that the information leakage from each individual query is negligible, while the joint query inject useful information into the system for classification. To design this system, we use the gradient descent algorithm. After the forward pass in the presence of the noise, we calculate the loss and perform backpropagation. The models of servers gradually learn how to mitigate the noise and achieve high accuracy. As you see, trained MPC is very efficient. In this method, each server runs a regular deep neural network. Also, it has a low communication load where the size of the queries and output are in the order of the image and label size only. In addition, there is no communication among the server. Indeed, the server may not even be aware of the existence of each other. Also, trained MPC achieve high accuracy with very few servers. Trained MPC relies on a semi-honest setup with n servers. All servers are honest, but an arbitrary subset of up to t servers may collude. In the training phase, the client having access to the training dataset and noise sample wants to design or train pre- and post-processing function in the client and functions of the servers and distribution of the noise according to the following optimization problem. In the optimization, we want to minimize the prediction loss. The constraint guarantee that information leakage through any set of T queries is less than epsilon. Furthermore, we desire that the computational cost of pre- and post-processing functions at the client are low. In the inference phase, the client follows the same protocol and uses the designed or trained system. In paper, we measure privacy with mutual information and differential privacy metric. In the first definition, we use Shannon's mutual information, and it states that information obtained about the client data by observing any set of tier-list query is negligible. In second definition, a strict differential privacy preserving, it states that the change of the client data in input has a negligible effect on the distribution of any set of tier-list query. Note that since a strict differential privacy is defined for any two inputs, which can be different in one pixel or a subset of pixels or completely different, it guarantees conventional differential privacy for two adjacent inputs. Here we present the proposed algorithm to deploy a realization of trained MPC. We use correlated Gaussian distribution for the noise distribution. The correlated queries is designed by adding client data to the correlated strong noise. We set the variance of noise large enough to guarantee negligible information leakage to the server. It ensures both input and output privacy. On the other hand, the correlation among the noise allows us to train the parameters of the model such that the client can mitigate the contribution of the noise by combining the answer of the servers. Note that such an opportunity does not basically exist in the approach using perturbation and adding noise. We train all of the network in the presence of the noise. The proposed method is as follows. The client passes data through a neural network and then normalizes the output. He adds Z1 to Zn to the normalized output and sends query 1 to query n to the servers. The servers apply a multi-layer neural network to the query and send the result back. The client using a neural network run a network over the summation of the answer to drive the label. Since the client has limited computational power, pre and post-processing function can be a neural network with one layer or even an identity function. We train the system in the presence of noise. In paper, we show that if we choose the standard deviation of the noise large enough, it satisfies mutual information and strict differential privacy preserved. Here, we report the performance of trained MPC for n equals 2 and t equals 1 versus adding noise for MNIST dataset. We evaluate our method for two models. In pre-processing, the client does not run any neural network. This means he sends data plus noise to server 1 and data minus noise to server 2. In trained MPC2, the client has a simple post-processing. And in trained MPC1, the client has no post-processing. In adding noise, the system with only one server is trained to label the noisy data. The figure shows that unlike the system with one server, trained MPC achieves good accuracy, even for a high noise level. In general, although the accuracy of the proposed method decreases with increasing variance of noise, but it still converges to a reasonable value. We compared trained MPC with adding noise and Arden, which is a framework based on perturbation and adding noise. Arden partitions a neural network across the edge and cloud and transmits the noisy representation of the data to the server. It trained the system on a mixture of the noisy representation and its clean and perturbed version. The figure showed that Arden, at the cost of computational burden on the client, improved the input accuracy slightly compared the adding noise approach. However, trained MPC outperforms Arden by 4% higher accuracy, 10 times more privacy, and 4 orders of magnitude fewer computation on the client. The low cost on the client side and the guarantee of good accuracy make trained MPC frameworks suitable for practical use case in mobile devices and IoT. In summary, trained MPC resolves the tension between privacy and accuracy while avoiding the computation and communicational overhead of multi-party computation and homomorphic encryption. As you see, the client with simple pre and post processing achieves high accuracy. Now we are working on more complex designs for those functions to achieve more accuracy. Thank you for your attention. Goodbye.
This is our first poster talk.
Shall I do it again? Yeah. So hello everyone, my name is Chen and I'm a fifth year PhD student in Rice University. And today I'm talking about the efficient and lightweight federated learning via asynchronous distributed dropout. And this work is like a joint work with MLSys Research. Okay. Yeah. So I will go very quickly about the background because we have limited time. So there's an eternal conflict between the increasing scale of deep learning with the limited resource. Like we have the model size, like the increasing of model size versus limited memory. And we also have the increasing computation complexity with a limited computation capacity. So we have we have invented several distributed training systems to solve this issue. The first genre is like the synchronous distributed training system, which is widely used currently, and they have data parallelism and monoparallelism. And there are also like asynchronous distributed training system that aims to solve something that haven't been handled by the synchronous distributed system. Is that we can have different clients or different computation device can have different computation capacity. And in the asynchronous systems, all the clients need to finish their work simultaneously, or we need to wait for the slow workers. So this is called a straggler effect, which will significantly increase the total training time if we are having like different computation speed for a different device. So thus, the asynchronous distributed training is very suitable for large-scale heterogeneous distributed training or federated learning systems. And I want to point out in the heterogeneous systems, each one can have heterogeneous communication training speed, or heterogeneous communication speed, or heterogeneous data collecting speed. Yeah, and we are facing the straggler effect in asynchronous training. However, in general, the asynchronous methods suffer from lower final accuracy, which I'll summarize in the next slide. So here is like the summarize the pros and cons from for the synchronous and asynchronous methods. And you can see here, each of them have some disadvantage in certain categories. For instance, the asynchronous method is like have high memory cost, high communication volumes, and high training cost, and with lower lifetime accuracy. So in this project, we want to devise ideal distributed system that can achieve like low cost and high final performance in all these categories. So when we like look into the asynchronous federated learning, we find out the performance, the worst performance might come from two main directions. I mean, two main aspects. The first is that because like we have in asynchronous systems, we have this gradient stillness problem, which is shown in the green circle here, which means that by the slower workers, we are generally using the gradient from the past iterations that are somehow older than the faster workers. So when the slower workers and the faster workers update their model and aggregate them together, they will have like the gradient from two different time steps. So this is called the gradient stillness problem, which will hinder the convergence of the overall model. And also because like we are in the federated learning scenario, each workers or each client will have a different like local data distribution, so the so-called non-ID data. So if you look at the blue circle here, the global model might overfit to the faster worker, which have like a more number of updates on its own local data. So this will cause the model drift to the local data in the client A. So we call this like the model drift problems or the gradient inconsistency problem. So there are several previous solutions to improve the asynchronous distributed training. To reduce the gradient stillness, people are using like a weighted update based on the gradient stillness from different like worker. So we just downweight the model update from the slower worker. But obviously this will not work well because like we are intentionally ignore the contribution from the slower worker. In the federated learning case, the slower workers might have its own distinct but valuable data set, local data sets. And to reduce the model drifting in federated learning, they are proposing some kind of like a regularization or some other methods that are applied to synchronous methods. And we'll show like later that this method cannot really solve the problems in asynchronous settings. So our key observations of the current method is that the current method do not improve much in the non-ID learning task. This is because we are sending 4 models to all the clients, regardless like their local data or their client computation capacity. So like for instance, like updating the 4 model will cause the global model to drift more significantly to the local model of the fast workers, which will cause like drop in the final accuracy. So our the key contribution here that we are proposing this asynchronous distributed dropout. We ask, can we select some models out of the global model and send this to each device, taking into account of the device heterogeneity? So in this case, we are not sending the full model to each device, but we are creating subnetworks from this full model and send it to each device. And be aware that this submodel is an independent subnetwork that can be trained on itself, and we can train it on the local data sets for each worker. And during the after several rounds of local training, we can synchronize them together and to form this a full global model without further training. Yeah, so for this, initially we are proposing this random subnetwork partition algorithm, and we have provided the convergence result for this async drop or a random async drop method. However, this such kind of submodel creation only passively help with the model overfitting and the gradient stillness problem, but it is not actively select the submodels based on the device heterogeneity and solve the fundamental inconsistency in the global model update. So we propose to resolve this inconsistency in the global model by balancing the contribution from different devices with a smart dropout method. So this idea of a smart dropout is by assigning model weights that we are assigning the model weights that are less updated to the faster devices. This way, less updated weight will be updated more frequently than random weight assignment, and vice versa. So, so briefly, we are just give a more controlled way of how we partition the subnetworks and train them on each device based on their computation capacity. Yeah, so the premise behind such protocol is that all weights eventually will be updated and will converge with a similar learning rate, with a similar convergence rate. And so this is our current experiment results on the CNN models. So there's so many baselines here. So let's just focus on the hetero async drop, which is the purple line here. As you can see here, the x-axis are the time, the workload time, and the y-axis are test accuracy. You can see here that because we are only sending the submodel to each worker, so we are saving a lot in terms of communication cost. And because we're only training on the submodel, we are also saving the training time locally. And so you can see here the purple lines achieves both better final performance compared to other asynchronous methods, and in most cases, and also it's always the fastest one to finish the training. And here are the detailed result table for our experiments, and you can always refer to our papers for the final result for the details. Yeah, and we also expand the current method to MLP and the LSTM models on other different type of devices other than the CV datasets. Yeah, so this is my conclusion that the async drop, because it inherits from the asynchronous method, so it have low communication frequency and no straggler effect. And because we are also creating the subnetworks and submitting to each device, we are also achieving the lower memory cost and lower communication volume, and and finally lower training cost. And by experiment, we show that this method, by using the smart dropout, we are balancing the contribution from each weight, which also solve the gradient consistency problem and gradient stillness problem, which also increase the final accuracy. So thank you, everyone. This is my presentation. Any questions? Yeah, thank you very much. Oh, that's it.
Sorry, I'm muted.
Oh, yeah, that's my question. Great, yeah, it's looking good. So, hi everyone. Here, I'm Nicola Fabra, I'm a PhD student from Italy, and I will present this work, which is over the federated TV learning. So, okay, so the main research question that we are addressing in this work is the following one. Can we provide finite sample analysis for federated reinforcement learning under communication constraints? In particular, we consider a multi-agent setting where we have n agents that are willing to train cooperatively a reinforcement learning algorithm. Our goal are to provide a finite sample convergence guarantees and to achieve a linear convergence speedup with the number of agents n, which means getting the benefit of the cooperation of n agents, which is of major practical relevance because, as you know, reinforcement learning algorithms are particularly data hungry, so they usually take a lot of samples to train. So achieving this speedup would be of major practical relevance. So what are the main challenges of this goal, to achieve these goals? One is Markovian sampling, which comes from the fact that in reinforcement learning, agents interact with an environment in a sequential way, and which is usually modeled as a Markov decision process. And providing finite sample analysis in this framework is particularly challenging. And another challenge is that in order to cooperate, agents need to communicate. And usually, especially in large-scale systems, communication is subject to constraints, as is the case, for example, in wireless networks, which is the case considered in this work. Federated learning has been widely studied in the last few years, and in particular, it is an instance of distributive optimization under communication constraints. And there is a large body of literature studying this specific framework under communication constraints. But what is known for federated reinforcement learning is that, well, apparently almost nothing is known. And so in this work, we try to contribute in bridging this gap. So we provide the first final example of convergence analysis for federated reinforcement learning under communication constraints, establishing a linear convergence speedup with a number of agents. So our contribution is the combination of these four aspects that you can see here. Very good. So we consider the most simple example of a reinforcement learning algorithm, which is temporal difference learning. We consider a Markov decision process with unknown dynamics. And we consider the problem of policy evaluation. So we want to evaluate a value function associated to a specific policy, which has the following, which is an expected cumulative reward and has the following form. So in practice, the state space can be very large. So as it is typically done, we resort to linear function approximation. So we have a covariance, a feature matrix, and an approximation parameter. And for each state, we will have an approximated value, so will be provided. The approximation will be provided by the approximation parameter theta, which will provide the linear combination of the columns of the feature matrix. And a very popular technique for policy evaluation in this framework is temporal difference learning, which is an iterative update rule. And you can see here, you can see that the iterative update rule of temporal difference learning is quite similar to stochastic reductions. But that GK, which is the TD update direction, has a key difference with respect to standard stochastic reductions set. And the main difference is in the data, because the data in this case is the observation process, okay, which is, as we were saying before, is temporally correlated. And in particular, the observation process forms a Markov chain. And so this makes the analysis much more challenging.
And indeed, only recently, from this update rule, finite sample analysis have been provided. And it has been shown that in capital T iteration, we can get an order 1 over capital T approximation in these recent works that I am listing here in the bottom of the page. Our research question again is in federated reinforcement learning with capital N agents. Can we obtain an order 1 over NT error under communication constraints? And the capital N multiplying the T at the denominator shows what we are hoping for, which is the benefit of cooperation, the linear convergence speed up with the number of agents. The federated TD learning framework can be summarized in the following figure that you see here. So we have N agents. Each agent is playing the same policy because the purpose of this agent is to evaluate a common policy. So they are playing the same policy and they are interacting with replicas of the same environment in the framework that we are considering. So they play the policy, they collect observations, and they compute update directions, which are denoted by GIK. So I is the agent and K is the direction. And as it is typically done in federated learning, agents will not share their private information, will not share their observations, their rewards, and their states, but they will share the TD update direction with the server. In this work, we have considered a wireless, typical wireless framework for this type of uplink communication. So at the moment in which an agent shares with the server their TD directions. And this framework is over-the-air computation, in which TD directions are transmitted as analog signals to the server, which receives the type of global update direction that you can see here, where we highlight the channel effects on the obtained global TD direction. We have a channel distortion for each agent, which is different for each agent, and we have a measurement noise at the receiver because we consider analog communication. Why is this framework particularly popular? Why is it so popular in the last years? Well, the reason is that it is very, very bandwidth efficient. And so in large-scale systems, it's very appealing in wireless networks because usually wireless network resources are quite constrained. The master, once it has received this global direction, can update the global path, and then we will broadcast it back to the agents. But the communication bottleneck, where the communication constraints are in this wireless setting, is the uplink phase in which we consider this over-the-air computation mechanism. That, as you can see, provides distorted and noisy versions of the local units. Our main result in this work is a finite sample analysis of this update rule. What we prove is an exponentially fast convergence to the best linear approximator of the value function, which we denote by theta star. And this exponential speed is consistent with what is known for finite sample analysis of reinforcement learning in the centralized scale. And the main takeaways of the analysis are as follows. So we can see what are the channel effects on the convergence rate explicitly. We have pH is the statistical power of the distortion, the channel distortion, and sigma tilde squared is the variance of the measurement noise at the receiver. And we also achieve, as we were hoping for, we achieve a linear convergence speed up with the number of agents. You can see that the statistical terms at the denominator have the number of agents n. And this type of writing is one way to see the linear convergence speed up, so the benefit of convergence. We also obtain a linear dependence on the mixing time of the matrix chain, which is tau. All the finite sample analysis that exist for reinforcement learning algorithms indeed assume that the underlying Markov chain mixes exponentially fast. So tau is a fundamental quantity in this analysis. And the fact that the dependency is linear is an additional value of our analysis compared with previous works. Because indeed, for the first time, we get in federated reinforcement learning, federated temporal difference learning specifically, a dependency on the mixing time of Markov chain, which is minimax optimal. To see what I mean, you can see we are comparing in this slide, we compare the previous work the previous existing convergence result on federated temporal difference learning, where the dependence of the mixing time was quadratic. You can see that how is squared. But we obtain a linear dependency of the mixing time in our work. This is another contribution of our method. So in conclusion, in this work, we provided the first convergence analysis of federated PD learning over wireless noisy channels. We established a linear speed up with the number of agents, so showing the benefit of cooperation in this framework. We established a novel improved convergence bound for federated PD learning, so this is also regardless of the channel effects. We have this, this is a result that holds regardless of the channel effects. But it holds also in the presence of channel effects, where we have an optimal dependency on the mixing time of the Markov chain. And future work includes more complex wireless models because we have adopted a widely adopted model for over-the-air computation, but we can consider more complex models. And we plan to extend this work to Q-learning. So instead of only policy evaluations, policy. And of course, also for Q-learning, there exists final sample analysis for the centralized case that we are taking inspiration from to the extension of federated reinforcement. We also have another work on this topic, which is in a digital, we consider again communication constraints, but in the digital communication case. And we consider quantization of the gradient directions and erasure channels. So this is all for my presentation. Thanks a lot. And if you have any questions.
So I have a small question. Don't necessarily share the reward, if I remember, but I'm curious, what is the reward policy? The kind of goal for the agent?
The goal, so what they want to do, what the agent wants to do is to evaluate the policy in this case. So the reward, the role of the reward is because the reward characterizes the value function. Because you want to compute the expected cumulative reward to evaluate the policy. So the reward could be whatever, like you're considering a general. I don't know if this answers your question. Does this? Okay.
Yes.
No, please feel free to reformulate your question.
So each participant in the FO environment has an agent assigned to them.
No, each participant is an agent.
Oh, okay. I was thinking the agent's like an edge, but
no. Agent is a federated element.
Okay, that clears it up. Thank you.
Oh, that's great. That's great. Any other question?
That's it.
Okay, so thank you very much for your attention.
Hello, this concludes our workshop on resource-constrained learning and wireless networks. This has been a great event with lots of new opportunities, lots of great discussions. So very good applications in resource-constrained computing environments. So this was great machine learning work. It was a pleasure to host this workshop. Going to conclude this right there.